Good morning, Rob and everyone. How are you?
Good morning.
Good morning.
Morning.
Okay, so it's 9 o'clock now, and I want to get things started so we can stay on time. I'm sure some people will come and go. Anyway, thanks everybody for calling in and attending this workshop on manganese bismuth tellurium materials. This is one of the first of several focused workshops on topological materials that are hosted by the CATS EFRC. And so I'm the director of CATS, and I'll do my CATS plug. Oh yeah, by the way, can you mute if you're not speaking? Okay, so the CATS is the Center for the Advancement of Topological Semimetals. It's BES Energy Frontier Research Center, and its mission is focused on discovery and understanding of topological materials, and so especially magnetic topological materials and magnetic topological semimetals. They possess unique bulk and surface properties not known in other materials, and so the EFRC has a goal to predict, discover, and understand these materials, and try to gain the capability to control transitions between different topological states. And so manganese bismuth tellurium systems are an exciting new materials platform for magnetic topological materials. It's kind of in the wheelhouse of the kind of things that we do in the EFRC. So, we pulled together this workshop with people who are working actively in the field and some people within the CATS Center who have the right expertise, I think, to push this research forward. And so, the goals we have for this workshop are, to get caught up to date on the latest research in these systems, to try to identify questions and research opportunities that we can capitalize on, try to get some collaborations together, and certainly continue discussing these things after the workshop is over. Just some quick rules. Please mute if you're not speaking. And then speakers, make sure that you're prepared to share your slides and stay on time. During the talks, if you have questions, sometimes it's difficult with these kind of video conferencing tools when you try to interrupt people. So what I found is useful is you can submit your questions on this chat feature during the talk, and then when the talk is over, we'll go through the chat feature and the people can, restate their questions, or I can read them and the speaker can address those. And then at the end of the workshop, we'll spend some time just having a general discussion about where we think opportunities are. So I wanted to take the opportunity for my my introduction to kind of give an overview of what I think are some of the key issues in this area. Of course, I'm an experimentalist, and I noticed after I put together the agenda for this workshop, it's a little light on the theory. So those who are theorists in the audience, feel free to interject what you think are some of the open issues here during the discussion time or asking questions. So, a lot of the motivation for development of these manganese bismuth tellurium materials is that, they're currently one of the best known example of magnetic topological insulator. And so topological insulators have Dirac-like surface states that are protective of time reversal symmetry. And so you see this Dirac cone, and then in real space, you have these spin Hall-like states which move around the surface. Introduce magnetic order that will gap the surface state. It breaks time reversal symmetry, so it will gap the surface Dirac state, and it can deliver these sort of unidirectional chiral orbits, which you can call this a Chern insulator, or you can call these orbits the quantum anomalous Hall effect. And so quantum insulators have these dissipationless edge states, which are topologically protected. And so there are several materials routes to magnetic TIs or the quantum anomalous Hall effect that are being studied. First route is called dilute magnetic semiconductor route, where you would add dilute concentrations of magnetic ions to known topological insulators such as bismuth selenide. And if you dope, say, a few percent of vanadium or chromium You can get ferromagnetic ordering up to 20 Kelvin in single crystals and thin films. And then the quantum anomalous Hall effect has been observed at sort of at millikelvin, maybe 100 millikelvin temperatures in those systems. Another approach is to proximatize a thin film of a topological insulator on a magnetic substrate. There's been some progress in that direction. You can see some references. The third route is to discover new magnetic materials, sort of intrinsic magnetic materials that are also topological insulators, and manganese bismuth tellurium is sort of the first example of one of those. Europium indium 2 arsenic 2 might be another interesting material that kind of fits that category, and that's another material also being studied in cats. So here, of course, we're in this workshop anyway, we're focusing on this third route. And by the way, there's a good review article by Takura came out last year on these magnetic topological insulators. Somebody is not muted. Can they mute? Okay. So magnetic TI can host a variety of different topological states that depend on the symmetry of the magnetic state. So as we discussed in the last slide, if you have a ferromagnetic topological insulator, it can host quantum anomalous Hall insulating state. Anti-ferromagnetic TIs can also host what's called an axion insulator state, or more generally, anti-ferromagnets can host what we call a magnetic topological crystalline insulator, where the surface electronic properties depend on the symmetry of the magnetic state. And also, if the bulk exchange coupling is large, you may close the TI gap and you would get a topological phase transition to a semimetal phase, like a Weyl semimetal. And so, what we're talking about here with manganese bismuth tellurium are these anti-ferromagnetic TIs. And so, there was some work done in 2010 by Mong and Joel Moore that kind of showed that if you have a topological insulator that has broken time reversal symmetry, and you can still have a symmetry, which is the time reversal symmetry operator times the half a lattice translation, which maps the anti-ferromagnet onto itself. And that if you have this, preserve this symmetry, it acts like a topological, it has a topological classification like a topological insulator would, a non-magnetic one would. And so surfaces that don't preserve this combined operation are gapped out. For example, if you have an anti-ferromagnet, the gap surfaces will carry a half-integer quantum Hall conductivity, and they can also carry this quantized magnetoelectric response, which gives you this E dot B kind of coupling. And so the other way you can think of these anti-ferromagnetic TIs is as a stack of quantum Hall layers, with this, this is not T to the 1/2, but T to the 1/2 would couple the shaded and the unshaded block. And these have opposite Chern numbers. So of course, the consequence of that is bulk anti-ferromagnetic crystal will be an axion insulator. But if I had, for example, a surface that had steps, I would find chiral edge modes on the surface steps where the Chern number changed sign. And furthermore, if I had odd layer systems, those would have a net Chern number, and so they should show the quantum anomalous Hall effect. So this is kind of an initial motivation to look for these materials, and manganese bismuth tellurium kind of fits all those categories. It consists of these septuple triangular layers, which is like a bismuth tellurium topological insulator with this manganese tellurium layer in the middle. And so the bismuth tellurium bands are inverted and topological, and the magnetic layers are magnetic, or the manganese layers are magnetic. And so the long-range magnetic order is anti-ferromagnetic. So I have these ferromagnetic planes which stack anti-ferromagnetically, and this T to the 1/2 operator which couples the magnetic sublattice. Finally, these materials, just like the bismuth selenides and bismuth telluride, are van der Waals systems. And so there's between these septuple layers are weak van der Waals bonds. And so what that means is that they're easily exfoliatable. So here's a picture of some microscope, these different flakes coming off the surface. And so this is good for studying surface properties in topological materials, because you can get clean surfaces, or like the proposal from the last slide, you can make few layer devices or odd devices where you can look for quantum anomalous Hall effect. So these
interrupt for a second?
Properties in manganese bismuth.
Rob, I think your slides aren't advancing when you think they're advancing for the rest of us.
It might be slow. It might take some time to, my internet connection isn't good.
Okay. Just so
Anyway,
you
I'll
can
put
say
all slides up afterward. I'll try to keep it. I just have to keep going on mine. I don't know what you guys are seeing.
We're on slide 6.
It's on slide 6?
Yep, that's what I have.
Oh boy, yeah, it's really behind.
Now I got 7.
How about that? I can try to reconnect. That'll take us about 5 minutes, and then I can finish. I can try to connect on my hotspot.
Well, or you can like send me the slides and I can put them up. Maybe that's faster.
What's that?
Well, you could send me the slides or put them on the box and I can put them up. Maybe that's faster than reconnecting.
I think it'll be fast to reconnect. Let me try.
Okay.
I mean, in principle, I don't even have to try a hotspot. I don't even have to disconnect. Is that better?
I don't know. We'll see.
What slide do you see now?
Well, I'm on 7.
Okay, now you are.
Not me. I don't know if anybody else has moved faster.
Still 7.
Huh.
We just move on.
Hey, Rob, this is a purely empirical comment.
No, it's it.
If you go out of display mode, it
Might be better.
it updates faster.
Oh, let's see. So let me.
It will probably help if the people switch the video off, which are not the presenter.
What's that?
People switch off the video to save bandwidth if they are not presenter.
Okay, let me try it here. And okay.
It says starting.
It's on slide 8.
No, it's just starting to share content.
Boy,
I
it's really
think
slow.
just go with it at this point. Or email
Well,
me.
I mean, that's part of the problem with these things is there ends up being some issue like this. So does it still
All right,
say
your magnetization and magnetotransport data are slide 8. Slide 8 is up.
Yeah, slide 8.
okay? Well, I think at this point we're just going to have to go with it. But so I talked about this manganese bismuth tellurium as being one of the best examples of an antiferromagnetic TI, and so just quickly run through some of the physical properties. So of course it is you see this A-type transition near 25 Kelvin. In addition, if you look at magnetization or transport as a function of field, you can see different metamagnetic transitions like spin flop transitions. So you can sort of control the magnetic symmetry with fairly small fields. Unfortunately, you know, it's not an insulator. It's sort of a poor metal, and you can look at the Hall data and you can see that it has N-type carriers. So if you really want to look at things like axion insulator, you have to sort of do some band tuning or some carrier tuning. So of course, the first thing to characterize the topological materials is to look at the surface electronic states. And so by ARPES, what you see there, of course, are these direct surface states in manganese bismuth tellurium, which tells you that it is a topological insulator. As the transfer shows, you have a Fermi surface, which is sort of above the cone, the point of the Dirac cone. So there are N-type carriers, and even on the surface, EF is not in the gap. And a big mystery is that, you know, these surface states remain gapless in the antiferromagnetic phase on the 001 surface. This should gap out. And so, you know, some challenges and open questions are, you know, we need to do some carrier tuning, I think, to see the axion and quantum anomalous Hall states. And why is there no gap, right? Is the surface really a uniaxial ferromagnet or something else? So, you know, one address sort of the nature of the magnetism is to look at the magnetic interactions using neutron scattering. So here is some data showing spin wave dispersion in manganese bismuth tellurium. What you see on the right are these, you know, sort of very weak interlayer dispersion, which tells you that you have quasi 2D sheets, and you have a uniaxial anisotropy given by the gap. In the plane, you see this unusual, it's not a cosine-like dispersion, it's more of a sawtooth, which tells you you have long-range interactions. So a big question is, what are the nature of the long-range interactions? And we also have some evidence for antiferromagnetic interactions in the plane, which would be a source of frustration. Is that important, especially for the surface magnetism? Finally, you know, we talk about exfoliated material, the quantum anomalous Hall effect. So, you know, if you have, again, you have an uncompensated magnetization. And so you can look in panel D here at these sweeps of the Hall resistance as a function of field. And for few layer, 3, 4, 5 layer devices, what you can see is layer devices have a ferromagnetic response. But all the layered materials at high enough field, when I align all of the planes, show nearly quantum anomalous Hall effect. And particular samples, which you could see on the very right here, you know, special samples or high quality samples, you can see the quantum anomalous Hall effect even without an applied field. And so there's some questions here, you know, regarding the surface states from ARPES is, why do you quantum anomalous Hall effect when the ARPES tells you that the gapped? Why is the transport gap, which is discussed in this paper, in the science paper, so small? Why don't all samples display this effect? There's clearly some quality issues. And what the paper demonstrated was that gating was crucial to see the quantum anomalous Hall effect. So the band tuning is very important. Going on a little bit, and I know I'm probably gonna run a little over, but I'll try to wrap up quickly. Have a whole family of these manganese bismuth tellurium materials which form natural heterostructures, and this consists of alternating bismuth tellurium quintuple layers and manganese bismuth tellurium septuple layers. So you have not only manganese bismuth 2 tellurium 4, but manganese bismuth 4 tellurium 7, which is the alternation of these quintuple and septuple layers. Manganese bismuth 6 tellurium 10, which is a septuple layer, 2 quintuple layers, and a septuple layer. And so you can get different magnetic ordering, different stacking of these manganese depending on the heterostructure. It could be ferro or antiferro. And of course, you get different surface terminations when you do surface studies. One thing that's will be discussed at the workshop is chemical tuning of manganese bismuth tellurium. So talked about carrier density. You want to modify that. You might want to change the magnetic ground state to try to get a Weyl semimetal. So in that respect, these antimony substitutions seem attractive. Antimony has a lighter atom. It has a lower average spin orbit coupling. And it modifies the carrier density. So you can see up here in the top right, the ARPES data for different antimony substitutions move the chemical potential into the charge neutral point. Also see that in the Hall data here where the carrier density, the carrier changes sign. And also you have a change in magnetic interactions. You can see here and magnetoresistance data, which show these spin fold transitions, which change their critical fields and so forth. And so there's a lot of things going on when you do this antimony substitution. And you can kind of compile this into a phase diagram as a function of antimony, where you sort of change from N-type to P-type through this electrically neutral point in the magnetic topological insulator. But as I continue to add antimony, I weaken the spin orbit coupling and the bands are no longer inverted. And so I have a topological transition from TI to a normal insulator. So at antimony, of course, you introduce disorder. So you have random bismuth antimony disorder, and the average spin orbit coupling control the size of the gap. But studies of these antimony materials have revealed other kinds of disorder which are important. This is anti-site disorder. So you can find manganese on the bismuth or the antimony site, and you can find vacancies on the manganese layers. And these seem to be present maybe in a low level in manganese bismuth tellurium. In manganese antimony to tellurium 4, they're pervasive. And what you get sort of on the picture here on the right are manganese which go into these antimony layers, which couple antiferromagnetically to the main layer. So each septuple layer is like a ferrimagnetic block. So the average magnetization is reduced. And even the interlayer coupling between septuple layers can be modified. And it kind of reminiscent of where we started, which was the dilute magnetic TIs, where I basically add dilute amounts of manganese into these bismuth layers, right? And so there's sort of a spectrum of these intrinsic magnetic TIs and the dilute TIs. And you can look at this paper by Rinks et al. Last year, where you actually show if you try to make manganese doped bismuth 2 tellurium 3, you actually end up forming more or less manganese layers. So there's some connection between the dilute ones and the intrinsic one. So I'm going to wrap up here. You know, what I think are some of the big questions. You know, can we get a quantized magnetoelectric effect in these materials? How do we optimize this quantum anomalous Hall response, which has been observed in the flakes? And can we obtain semi-metallic phases such as Weyl phases by tuning the magnetic properties? There are materials issues. You know, can we use this chemical tuning advantageously? How do we deal with vacancies, impurities, and anti-site exchange? What do we understand about surface disorder and surface magnetism? Do they play a role in whether these Dirac points are gapped? And, you know, how much real, you know, control of these materials and the topological properties will require the development of thin films or multilayers? And one thing is that we talked about, you know, these advantages of manganese bismuth tellurium. We also talked about antimony doping, but you know, we didn't talk about other magnetic ions, europium, vanadium, polonium-based compounds, or selenide. So there's a lot of additional things. So that's all I had for my intro. I'm more or less on time, but I didn't leave too much time for questions. Let me stop. Are there any questions? Did anybody put anything in the chat? Try to stop sharing here. Let's see, open the chat. Questions? I didn't see any specific technical questions in the chat.
Hey, Rob, I have a question. So
Yes.
how would you measure topological magnetoelectric effect?
How?
Yeah, what measurement are you thinking of doing?
I mean, I'm hoping that somebody can tell me. I'm a neutron scattering guy, right? I mean, I think basically, you know, it's like basically it should act like a multiferroic, right? So you should be able to see in an applied field a ferroelectric polarization or vice versa. And so you would have to, accounting for other types of non-topological responses, be able to discern that quantized. But how you would actually, you know, hands-on in the lab do it, I don't know. Maybe somebody has an answer for that.
Well, I mean, you could imagine applying a magnetic field and measuring some kind of lattice response along the same direction as the field, for example, or charge response, right? So it's a topological magnetoelectric effect. That's what we're talking about, right? It's an electric polarization response along the direction of a magnetic field, or a magnetization response along the direction of an electric field. So you would perform a measurement that way.
I'm really just wondering, you know, how you measure. What would you if you, let's say, apply a magnetic field? How can you measure? I guess you need a thick film.
Yeah, a thick film, or I guess you could try to use a bulk crystal. I'd imagine you could do some kind of diffraction experiment, or maybe some dilatometry. I don't know. It might be easier to do the measuring magnetization in the direction of an applied electric field. That might be an easier experiment to set up.
So Rob, it strikes me that any questions about magnetoelectric effects would mean that we'd have to optimize how insulating the material really is and the defects. I also wonder about whether there are optical measurements that are proxies for doing those sort of measurements.
Rob, you there?
So I think we should move on to the next talk. And again, if you're not muted, mute. I'm getting some there. Okay, I think I'm muting everybody that's not muted. And Yan, why don't you get your talk ready? I think I found the culprit. Yeah.
Okay. Can you hear now?
Yep.
Okay.
Sorry about this. You know, these are always these technical issues, but
Yeah.
so yeah, share your slides and
let me share my screen.
I'll try to keep time, but I know we're already running late, but that's kind of expected.
That's fine. I don't need to go over the first two slides, so that will save some time. You already showed the data. Let me see. It's kind of slow. Could you guys see my screen? No.
Yes.
Yeah.
You can see it now.
Yes, we see it. Slide 1.
Slide 1. Cool. Let me go to the slide mode. Can see it now?
Yes.
Okay. This is slide number 1, right? Could you see the slide change? Oh, okay.
Yeah,
That's
it's working.
So it's better than yours. Okay. I'm Ian from Oak Ridge. Well, thanks for organizing this workshop. It's pretty cool. Thanks for the great introduction about the overview of the work. And what I will talk about is the defects in this compound. And I don't think I need to go over the first 2 slides. But one thing I really want to mention is if you look at the magnetic susceptibility or the temperature dependence of magnetization and field dependence of magnetization, especially this curve, this figure. I really like it. It's like textbook-like. It's pretty cool. And these have, as Professor McQueen said, has dramatic effect on the transport properties. And if you look at this panel, this material is kind of like a bad metal. It definitely has some defects, and all crystals grown by different growths are N-type with the electron concentration about 10 to 19th or 20th. And this is a good sign. This material is like bismuth-2 tellurium-3 may have quite some intrinsic defects, and this would control the type and concentration of charge carriers. So the work I'm focusing on now, or the questions I've tried to address recently, are these related to defects, lattice defects. What intrinsic defects are likely in this compound? And topological properties mean robust against the non-magnetic defects. What happens to those magnetic defects? Because we have magnetic manganese ions in this compound. And what kind of effects these defects would have? Are they good or bad? And finally, is there any way to get a good control of this after understanding why they form, in what situation they form, and in what kind of effects we would have? Well, whether we can choose some special defects. Those are the questions I try to address, and basically I put the 3 on the right. It's identify, understand, and finally get control of the lattice defects. Just like what Professor McQueen said, is that they're mainly for the band tuning or the carrier control. I talked with my neighbor, Mohua Du, who is a theorist working at Oak Ridge. I said, what kind of defects are likely? And he did some DFT calculations, and these panels show the formation energy of low energy defects. This is the formation energy versus the Fermi level, and he calculated that of 124, 147 in tellurium-rich case and in tellurium-poor case. And for those positive, the red ones with the positive net charge, it's positive slope, blue ones, negative slope. Most important results here, at least the DFT calculations, the bismuth at manganese side is the most stable donor defect. And manganese at bismuth side and bismuth at tellurium side are important acceptor defects. These are the defects that we need to pay attention when making the crystals and understanding the properties of the crystals of the samples, either in bulk or in flake. And if we think about the manganese vacancy or tellurium vacancy or bismuth vacancy or interstitials, they have quite high formation energy. So we do not need to worry about those lattice defects too much. If we compare 124 versus 147, let's look at the bismuth at manganese side. The formation energy for 147 is lower than that in 124. And it's interesting, we know the size difference between these 2 ions are pretty large. Manganese 2 plus is 0.83, bismuth 3 plus is 1.03. And it turns out there are quite, if we look at the in-plane lattice parameter of these phases, manganese Te, 124, 147 to bismuth 2 tellurium 3, and the in-plane lattice increases, which means when you put these together, manganese Te and bismuth 2 tellurium 3 together to form the natural heterostructure, the manganese Te layer is under tensile stress, and bismuth-2-toluene-3 is on the compressive stress. So this facilitates the formation of bismuth manganese andesite defects. These are from DFT calculations. What we observed in experiment in lab. Here I show the STM image of manganese bismuth-2-toluene-4. This image was taken by Weyl, and he could see the surface, the defects in the surface layer. One is like what he observed is the bismuth-toluene, bismuth at toluene site, and mainly manganese at bismuth site, about 3%. If we look at the elemental ratio of different crystals, and here I list the composition of 4 different crystals. One is from Dresden, the other 3 from our lab. And the crystals can be really manganese deficient, bismuth rich, or it can be close to the stoichiometry. And so not all high quality crystals are the same, no matter how high quality we claim when we send an email to you guys. So the stoichiometry is pretty sensitive to the growth parameters. And now we are trying to develop the relation between growth, chemistry, and properties. When we go from 124 to 147 to 1610, and we can see the manganese deficiency, there are more manganese deficiency, and the crystals become more bismuth rich. All these crystals are made out of bismuth-toluene flux. And so this, according to Mohua, the DFT calculations is due to the larger lattice mismatch between manganese Te and bismuth-2-toluene-3. Now let's back to think about that 3% of manganese at bismuth site. And we know in bismuth-2-toluene-3, 3% of manganese at bismuth site is enough to induce a ferromagnetic order. And how about in this compound? We checked magnetic properties. We tried different ways. This is a stability, this is a stability. We tried different ways to try to find evidence for the magnetic order of that 3% manganese. So far, we don't see any good evidence. We don't have any good evidence. And so one question is this just too little for this compound? 3% is not enough. When we are working on this, bismuth one, we also look at the antimony 124, manganese antimony 2-toluene-4, which is iso structure. This is also DFT calculation from Mohua. If you look at the formation energy, the formation energy of manganese at antimony site is slightly negative. This means this defect will form spontaneously. And also, if you look at the anti-site pair, antimony at manganese site, manganese at antimony site, and the formation energy is also small, close to 0, which means in this compound, there may be more manganese antimony site mixing. And also, if you look at the energies, the formation energies, it favors the accepted defect, means this explains why this compound is p-type when we made out of lab. So this antimony 124 might be a better system to study the possible magnetic order and also the effect of this magnetic order of magnetic defects. So we made crystals differently, try to the flux growth at different temperatures. Here I show the magnetic properties. These the left 2 panels show the temperature dependence of magnetic susceptibility. And if the crystal is grown at 620 degrees C, it shows the antiferro-like temperature dependence. But if we increase the growth temperature to 640, it shows a ferromagnetic like temperature dependence. And the right 2 panels show the field dependence, the magnetization. There's a spin flop when the field is applied along the crystallographic C-axis, but is absent for this one in the panel F, which shows a ferro-like magnetic susceptibility. So what happened? Why they're so different in these two crystals? Crystals look like the same, beautiful. And if you look at the anisotropic properties, the magnetic order should have the moment aligned along c-axis, like bismuth 124. So we then look at the crystals, both crystals, actually not both, as many more compositions with different TCs. We look at the crystals with neutron single crystal diffraction. And the refinement suggests, yes, there are quite some site mixing. Here I show the composition and occupancy of this one, and also also the other composition, the composition and occupancy. And they're like 40% manganese replaced by antimony, and they're like 15% antimony replaced by manganese. And this composition, or the overall composition, agrees pretty well with those obtained from elemental analysis. And it turns out we have to consider the magnetic order of manganese at antimony site, because now we have, where's my mouse? Well, I'm sorry, I couldn't find my mouse. Okay. It's in the manganese at antimony orders magnetically. In each septuple layer, it forms the ferromagnetic arrangement. The interlayer coupling for the top two panels, and the interlayer coupling is a ferro. And for the one which shows antiferro-like temperature dependence, and the interlayer coupling is antiferro. And we then checked crystals grown differently, trying to control the manganese content and occupancy. We find not only the sign of the interlayer coupling, but also the transition temperature can be finely tuned by changing the manganese content and occupancy. Okay, we then look at carefully with some local probes, STM and STM, trying to understand how those magnetic defects distribute on the top layer. And this is the STM work by Weyl, he's in the audience. Here the STM work by Neutron and CMS. The beautiful images tell us there are no other defects really observed, but there's a manganese antimony site mixing, and most importantly, it's a uniform distribution or the random distribution. We didn't see clustering of those magnetic defects. Then what happens to the band structure? We know there are enough manganese at antimony site, and it forms magnetic order, induce the really complex ferromagnetic arrangement. What happens to the band structure? Here I show the images from Lin. I think he's also in the audience. For the ferromagnetic manganese antimony 2-4 without any site mixing. Yes, there's a Weyl point here. But once we introduce the site mixing, look at the panel D, that Weyl point is gone, or if there's a gap opening. It doesn't matter whether it's ferro interlayer coupling or antiferro interlayer coupling. And once we introduce site mixing, and this calculation tells us it's not good for the band inversion, which means the anti-site mixing or the site mixing here really engineers the band structure, not good for the non-trivial topology. Okay, here are what we learned from manganese antimony 2-4. Random distribution of a lot manganese at antimony site, orders, bad for the band inversion. And one thing I didn't develop is actually this ferromagnetic alignment in each septuple layer actually explains the difference between ordered moment and saturation moment. The ordered moment at 4 Kelvin is about 4.5 MnBi. the saturation moment at 2 Kelvin, 7 Tesla is about 2 MnB. It's quite different. It's only half of that. It's actually the saturation moment here. The field is not large enough to polarize all magnetism moment. So what we observed as 7 Tesla actually is the net moment of that ferromagnetic arrangement. Okay, these are what we learned. Now let's try to apply to the manganese bismuth 2 term 4. The saturation moment at 2 Kelvin is 3.6 MnB. The order moment is 4.5. And why they are still different? And normally, we expect the saturation moment is larger than the order moment. So it is a good sign for the magnetic order of manganese at bismuth site. And if not, as I said earlier, we didn't get good evidence for this. If there's no magnetic order, what happens to that saturation moment? And do we still need to go increase the concentration of manganese at bismuth site, or try to introduce, for example, chromium or vanadium to the bismuth site to generate that ferromagnetic structure, try to see what kind of properties you could get, or what bad things the defects would do. And also, these magnetic defects on the really top layer, they really relate to the gapless feature from the photo emission. We don't know. That's definitely something we need to figure out. Okay, before I get to the last slide, I would like to show you some preliminary results, how we use the defects to control the transport properties. From the DFT calculations, tellurium-rich environment would be a good way to control the electron concentration. And here I show if we change the bismuth-tellurium ratio in the flux, add some extra tellurium, and we could control the electron concentration. And antimony doping is the other way. It's the extrinsic defect. It's a really valid one. With good control of the stoichiometry and possibly the occupancy, that's something we need to figure out with antimony doping, how much anti-psi is induced. And we can really make the crystal less conductive, and this kind of like a semiconducting or bipolar behavior. Okay, to summarize, it's important to understand the defects, to understand why firms, what kind of defects firms, what effects they have, and finally to get control of these defects to do the band tuning or the carrier tuning. And this is not an easy job. You need really multiple pros, close collaboration between different groups with different expertise. And so if you're interested in this project, please let me know. Finally, I would like to acknowledge all my collaborators on the manganese antimony 2 term 4 project, helping me figure out all the problems with the antimony crystal. Thank you.
Okay, thanks, Yang. So we have a few questions came in on the chat. Yeah. So Lin has a question. How about tellurium vacancies and the formation energy?
I think that energy is also pretty high. In the figure here, I showed only the low energy defects. And in the paper we posted archive last night, it shows in the supporting document, there's the formation energy of the high energy defect. And I think the tellurium vacancy has much higher formation energy.
Okay.
So I had the next question. So how large of a field did you apply to the, sorry. Okay. Question was from me, and it was, how large of a field did you apply to the manganese antimony to tellurium 4 to look for a fully aligned ferromagnetic state?
At 12 Tesla, we still cannot see it. And we try to go to Tallahassee to get more to higher fields. It seems it should be over 20 Tesla, but we need more measurements to confirm.
Ferromagnetic coupling between the main manganese layer and the manganese in the antimony would be quite large. I mean, it's the largest magnetic energy scale in the problem.
Yeah, it's very, very large compared to the interlayer coupling, definitely.
Okay, so one more question from Weyl Wu. Why site mixing gap in the Weyl semimetal state in DFT? Is it a TI or an NI?
Well, Lily,
from the calculation, so it's the NI. I think the problem why it gapped up to the Weyl points is because the this side mixing is the concentration is so big. So basically you have like a single row of this magnets in the antimony layer that somehow breaks the bonding between the antimonies, right? So I think that it has something to do with the high concentration of that.
Okay. All right. Any other questions? We'll move on to the next talk, which is from Simon Riberos, and a talk about neutron scattering, investigation of magnetic orders. So yeah, you can stop sharing and then Simon can share.
How to stop sharing?
Hey Rob, can I just ask a quick question? Sorry, I had to log out and back in again because I don't know why WebEx was having an issue. So has anyone done the doping, for want of a better phrase, but the substitution of selenium for tellurium? So in the non-magnetic bismuth selenide, bismuth telluride, that was one way that they got control of how insulating the bulk was, as well as the antimony doping and things. They did the stoichiometric mix in the quintuple layer. Has anyone done this here?
I tried. This is Ian from Oakridge. I tried to dope it with selenium. Once we put selenium in, manganese selenium is a competing phase, which means selenium will grab manganese and precipitate out first.
Got it. Okay. Just a thought.
Okay, can you hear me? Can you see my slides?
Yes.
All right. Okay, I'll start then. Good morning, everyone. I'm Simon Riberos. I am a postdoc working at Ames Lab with Rob McQueenie, and I would like to present you the magnetic properties in the manganese bismuth 2N and tellurium 3N+1 materials, and in particular in the antimony doped manganese bismuth 2-X antimony XTE4. So this is this compound series, and so this is the N=1 variance of this formula above. Can you see my mouth? For some reason it doesn't work. Well,
yeah.
Okay. I can't see it, whatever. Let me continue. So I also like to say that a significant part of the content that I will actually be presenting here is actually the work of Jan from Oakridge. So this is the layout of my talk. I'll start by a presentation of the crystalline structure of this manganese bismuth 2N Te 3N+1 materials. Then I'll be introducing their magnetic properties. And then I'll go through a neutron scattering investigation of the antimony doped manganese bismuth 2 Te4 variants of this family. And so I'll present the crystalline structure, the implication of the doping on the crystalline structure, and on the magnetic properties of this compounds. So first of all, I'll present you the crystalline structure of the manganese bismuth 2 and tellurium 3N+1 materials. So this was investigated by Jan and his collaborators, and also by Ding and collaborators. So these materials are Van der Waals layered materials, and so they consist of triangle layers of manganese, bismuth, and tellurium atoms that are stacked along C. And if we look at the compounds themselves, we can see two different types of building blocks. The first one labeled as A here is called the quintuple layer, which consists of bismuth and tellurium layers and are not magnetic. And now if you introduce a manganese tellurium layer in the middle of these two layers, you obtain the septuple layer displayed below in B, which is magnetic. And if we look at the crystal structure of the n equal 1, 2, and 3 variants of this family, which are the 1, 2, 4, 1, 4, 7, 1, 6, 10 variants, we see that for the 1, 2, 4, n equal 1, we only have we only have septuple layers which are stacked on top of another, only magnetic layers. And if we go to n equal 2, we see that in between the magnetic layers, we start stacking the non-magnetic quintuple layers, so only 1 for n equal 2, and n equals 3, we have two non-magnetic layers stacked between the magnetic layers. And so there are studies that suggest that n can actually go up to 6, so we'll have 5 non-magnetic quintuple layers stacked between every septuple magnetic layers. There is also a general stacking rule which has been proposed by Ding and his collaborators. So this stacking rule is based on the rhombohedral symmetry of the bismuth tellurium material, in which the structure is here represented. And as this structure is here represented as the stack along C of different building blocks which do not correspond to what I was previously describing. This is another type of labeling. We here have A, B, and C type of bismuth tellurium layers as presented on the figure. And according to the symmetry of this material, we can actually change the sequence, the ABC sequence. And here we're also interested to stack manganese tellurium layers, which are magnetic in between the ABC type of layers. So this gives rise to many different possible combinations. And so the combination going for n equal 1 to 6, published by Ding et al., are here presented at the bottom on this table. So we see that for the n equal 1 manganese bismuth 4Te7, we have this CBA type of stacking separated by magnetic layers. And for n equal 2, the 147, we just have A and C type of layers separated by magnetic layers. So this rule works for every possibility, and we can see that there is many different possibilities in this family, structural possibility in this family. We can also see that the capping can either be magnetic, as for n equal 1, or non-magnetic, as in the n equal 2 case, and this will influence the surface state of this material. If we now look at the magnetic properties of the members of this family, from susceptibility measurements, it was reported by Jan that the ordering temperature for the 1, 2, and 3, n equal 1, 2, and 3 variants of this family are 24, 30, and 11 Kelvin. Also, we have dominant antiferromagnetic correlation as positive Weiss constants were measured, which means that the also we have effective moments of about 5 MnBi per magnetic ions, which are measured. So this means that the manganese ions have a valence 2+, and they are in their high field state with S equal 5/2. Also, there is Jan made interesting magnetization measurements with H applied along C. So if we look at the top panel for the manganese bismuth 2Te4, with the data collected at the lowest temperature 2 Kelvin in blue, we see that at about 30 kilo-Oersted, we have a spin flow transition for H applied along C. And so this means that the spins actually rotate from a direction parallel to the C-axis to a direction perpendicular to the C-axis when we apply the field. And then this is followed by a progressive polarization of the field of the moments along the C-axis. If we look at the second panel, we have the corresponding measurements for the 147 in A and 1610 in B. So if you look at the blue data and zooming in this hysteresis curve, we see that when we apply the field along C, we don't have anymore this spin flip transition, but it's replaced by just a spin flip transition. So the moment will not get perpendicular to the field. And this happens at about 1.5 kilo-Oersted in both cases. Now, if we can focus on the magnetic ordering, which is stabilized on those materials. So for this, there have been neutron scattering measurements that were performed, And the result is that actually every members of the summit that were investigated with n going from n equal 1 to 3 do stabilize the same type of magnetic order, which consists of ferromagnetic layers which are in plane with the moment pointing along C, and each adjacent layers is stacked along C antiferromagnetically. And this also imply a doubling of the crystalline unit cell. The ordered moments at 6 Kelvin for n equal 1 to 3 were reported to be equal to 4, 3.58, and 3.55 respectively. And also like to mention that in the manganese bismuth 47 case, there's a tiny bit of moment in plane, which is about 0.15 MnBi per manganese ions. From this result, we understand the magnetic properties of this material as being the result of interlayer exchange interactions, which I label as JC and that are antiferromagnetic. So they couple the layers along C antiferromagnetically. And there is a competition between this interaction and the single ion anisotropy labeled as D, which induces the ferromagnetism in the plane. It is calculated that actually JC decreases drastically with n increasing because the distance between the magnetic layers increases with n. However, D is actually less affected. So the interlayer magnetism is dependent highly on D. So we expect that it should not be that affected as n increases, as the distance between the layer increases. And consequently, when we reach the large enough distance corresponding to a large enough number of n, we expect a fully ferromagnetic structure to be stabilized. If we now focused on the antimony doping of the manganese bismuth 2Te4 material, so it's the n equal 1 variant of the material I was discussing before. Actually, the manganese bismuth 2Te4 materials are heavily electron doped. So we need to fine-tune the Fermi level by doping to actually activate the interesting topological properties of this material. So in this case, we introduce antimony ions at the bismuth sites with the objective to tune the band structure without influencing too much the magnetism in the manganese tellurium layers, which are here in green, the figure on the right, and the bismuths are in blue. So this has been investigated by Jan, and he also synthesized the samples for various doping concentration, going with X ranging from 0 to 2, with 0 being the manganese bismuth 2Te4, and 2 being the fully antimony doped manganese antimony 2Te4 material. So Jan also reported characterization measurements. So first of all, from transport measurement, we see that there is a crossover going from A-type to P-type at X concentration, which is equal to about 0.63. Also, on the first panel on the right A, we see that the ordering temperature actually decreases with the concentration of doping, which is due to the fact that actually JC decreases with doping. So we have more competition occurring in between single ion anisotropy and exchange interactions. If we look at mu effective, the effective moment, it remains rather constant, which means that the spin state in the material, the spin state of the magnetic ions is unchanged. If we look at the third panel, this is the evolution of the bi-station. So we see that actually this is also decreasing drastically and becomes negative, which means that the dominant interactions change from antiferromagnetic to ferromagnetic. Also, we have saturation, the panel D, we see that the saturation moment decreases with the concentration. And panel E, we also see that the critical field for spin flip in red and spin flip in green do decreases also with concentration. And from all those magnetization data, we see that this suggests that both JC and D single ion anisotropy do decrease as a function of X. So we were also interested to investigate the magnetic order stabilized in this different doping concentration of the material. So we investigated, for this we performed Newton scattering experiments on polycrystalline samples at Oak Ridge using the Padron instrument. And we investigated doping concentration going from X equal to 2, which is manganese antimony 2Te4, down to X equals 0.5. So from data collected at 100 Kelvin, we investigated the effect on the crystalline structure of this doping. And one of the important results that we have that was just mentioned also by Jan is that the sample we investigated for manganese antimony 2Te4 actually has a lot of site exchange between manganese and antimony. So here we find that there is about 20% of manganese at the antimony site and 40% of antimony at the manganese site. If we now look at the other concentrations that we have investigated for X equal 1.5, 1, and 0.5, in this case, we do not have any manganese sitting at the bismuth antimony site anymore, but we have a lot of bismuth going to the antimony sites. So in this case, we find that we have about between 16 and 21% of bismuth going to the magnetic antimony site. So from data collected at 10 Kelvin, we have refined the magnetic structures of these materials. So first of all, in the manganese antimony 2Te4, we find this, so here as I said, we have a lot of manganese going to the antimony site. So we find a K equals 0, 0, 0 magnetic order with the moments aligned along C. And here, both the manganese sitting at the manganese site and the manganese sitting at the antimony site do actually order. So we have two different types of magnetic sublattice, which are represented in red and blue. And those sublattices are ferromagnetic, but they're with the moments aligned along C, but they are aligned anti-ferromagnetically, one with respect to another. For the concentration with X equal 1 and 0.5, we have a similar order to the manganese bismuth 2Te4 case, with the structure represented on the right side. So again, this will be ferromagnetic layers in plane, aligned, stacked anti-ferromagnetically along C, with a doubling of the crystalline unit cell. In the 1.5% doping case, the results are not very clear because we only see one magnetic peak, which is tiny. However, this peak can be indexed with the same propagation vector as in the manganese bismuth 2Te4 case. So by continuity, we expect the same type of magnetic order as in the manganese bismuth 2Te4 case here. So if we, from the refinement, we have obtained ordered moment per manganese ions for the concentration 0.51 and 1.5 equal to 1.6, 1.5, and 0.9 MnBi. So this is fairly small, and I expect that one of the reasons for this is the fact that we have a lot of bismuth going to the manganese sites in those materials, and the samples that we have investigated were not the highest quality also. To conclude, I will say that we have A-type anti-ferromagnetic ordering with the moment pointing principally along C observed in all the different variations of manganese bismuth 2 and Te3 and +1 compounds that we observe. So this means with N ranging from 1 to 3. The magnetic properties are strongly influenced by an increase of N, and ferromagnetic order is expected for N probably above 4, since we didn't study this one. Antimony doping of the manganese bismuth 2Te4 by reducing both the JC exchange interactions between the layers and the interactions and single ion anisotropy interactions, and strongly influence the magnetism in those materials. The most interesting, well, not interesting, but the one that is most strongly modified is the manganese antimony 2Te4, which actually stabilizes a different magnetic phase than the other members of the family due to a strong manganese bismuth site interchange. With this, I'd like to thank you for your attention.
Thanks, Simon.
Is there questions?
So we have a question in the chat from Alan McDonald. Why do you identify the anisotropy as important for the intralayer instead of the intralayer exchange energies?
For the interlayer or intralayer? I can't see the question for some reasons.
I think there's a statement there that you said the uniaxial anisotropy controlled the ferromagnetism. Am I getting this right, Alan?
So
Yes, that's right. So you can see it on the conclusion there, the third line. Why do you emphasize D? Is there a special reason from your measurements?
so this will be. So I presented. So why? Sorry, I'm getting confused. So there is actually a bit of D actually decreases as a function of doping, and the magnetization actually decreases also.
So how do you measure D?
So D was estimated from a calculation from the critical spin flip field and spin flip field. So
Okay.
yeah.
From if I can step in, so right,
Sure.
so if you have D, and so JC, if it's antiferromagnetic, and D is large, then you'll get a spin of stabilize the antiferromagnetic phase. But if D gets small, then the applied field necessary to fully align all the layers becomes extremely small. And you end up, rather than having a spin flop, you just have a spin flip at a weak field, which goes straight into the full ferromagnet. But of course, you wouldn't have it if the intralayer exchanges weren't ferromagnetic. And of course, that has to be true.
Yeah, so this is the same as in the -2 and TE3 and +1. As you increase N, actually JC drastically reduces, and so you go from the spin flux transition disappears. You don't see it anymore when N is equal to 2 or 3. You see the spin flux transition with N equal 1, and in this case, it's JC that decreases where D is not that much affected, and so it's a reduction of JC, especially that suppresses this spin flux transition, as I understand.
Okay. Any other questions for Simone?
Yeah, Simone, this is Ross. When so you reported a change of sign of the Curie-Weiss temperature, is that right?
Yes.
Do you also see an onset of magnetic hysteresis once you get to the ferromagnetic side? Maybe I missed it.
1 second. For some reason, I can't see my slides anymore, so I'm getting a little confused. Oh,
We can still see them.
I don't know what I did. I'm not used to this web text, and unfortunately. Can you please repeat the question?
So
Well,
I remember you showed, and it was one of the small graphs showing the different trends of the magnetic properties with doping. You showed the change of sign of the Curie-Weiss temperature. Is that right? From a susceptibility measurement?
Yes.
Okay. So my question is, once you got to the ferromagnetic side of the Curie-Weiss behavior, do you also see an onset of hysteresis in the M of H sweep?
I don't know about this. Maybe
okay.
knows that because this was the measurement done by Jan. So, but what it's clear here is that since the Curie-Weiss temperature changes, we go from strong, from dominant axion interaction in the system to probably dominant single ion anisotropy, which are ferromagnetic. I guess that's probably the main message here. Maybe Jan knows the answer about the. Jan, are you here? Because it's measurements.
Yeah, can you hear me? I try to.
Yeah, we can hear you.
The Weiss constant really changes sign, but all those compounds still order antiferromagnetically.
Okay.
And
because sometimes you get quite complex behavior where for one orientation it looks like you have a ferromagnetic like Weiss constant, in another it may still be antiferromagnetic. Yeah, especially if something's frustrated.
We didn't say that.
Okay.
Yeah, it's pretty isotropic.
I think like if you look at 147, you have a very small spin flop field. And so you can get quite complex M versus H behavior because it's easy to get into the ferromagnetic phase. You can get these complex hysteresis loops. And there's a PRL on that that just came out a month ago or so, where you can use this Stoner-Wolfarth model for ferromagnetism, and you can understand basically the field evolution of the magnetization that way. I don't know if that's addressing what you say, but it is an anti-ferromagnet, but you can still get ferromagnetic-like hysteresis loops, especially in 147, where the interlayer coupling is extremely weak.
Okay, thanks, Rob.
Mm-hmm. Let's see, we have a couple more questions here. So Anand Bhattacharya has a question. How easy is it to synthesize higher end samples? Does it get harder to grow smaller window of conditions? I don't know if Yan, you want to.
I can answer that. Yes, it's much harder to make a higher end samples. And at this time, we can reproducibly make 124, 147, 116, but we really don't have good understanding of the growth mechanism. We start everything the same, but changing the temperature profile just slightly, we can get different phases. To get 813, let's go to even higher end. You never know what you would get.
So do you have a feeling for the sorts of defects and things that creep into your sample as you go up in N?
It becomes more manganese deficient and bismuth rich. Becomes worse and worse. So if you really want to look at the transport properties of those flakes, those compositions, be really careful about the defects. You might get really bad sample.
But it's interesting that when you get to the higher ends, like I think N equal, well, the 1,813, I know there's published work on that, but you're basically approaching a manganese concentration, which isn't very different from the dilute bismuth telluride, bismuth sulfide materials. The Mn concentration about the same. And so these anti-site exchange, it starts to look, you might get sort of a disordered quintuple layer TI, actually. Question, did you want to?
Oh yeah, just it was very interesting to see the evolution of with antimony doping, and I'm just wondering if there is any what evidence do we have right now that, and I just don't know the literature well enough, the manganese antimony tellurium compound, that it's topological. Is there good ARPES data or any transport to suggest that's the case?
And I don't know the answer to that either. I think it's predicted to be not topological, but whether that's verified experimentally, say, like you say, by ARPES or something, I don't know. Maybe somebody in the ARPES crowd might know. There's an ARPES talk coming up, and maybe we can ask then.
So is there a topological phase transition with antimony doping then? At some point, does it stop being topological? Is that the belief?
It's about half-half.
Half-half.
Yeah.
But is that experimentally proven to be the case, Jan? Do you know?
Yeah, there's a work from Nanjing University, and they did some measurements. Not complete, but they went through the whole series.
Cool, thanks.
Yeah, sure.
Okay, we should move on to the next talk. So that's by Alan McDonald, a simple model for MnBiTe family of magnetic topological insulators. So Simon, you need to stop sharing. And then after Alan's talk, we can have a short break.
So are you seeing my screen now?
Yep.
Okay, so I'm taking someone's advice and showing the slides on the left. I'll just do it this way. So this is what I'm going to talk about is a project I got interested in from my interaction with cats, thanks to all of you. And the hard work is done by a postdoc at UT Austin, Chao Lai, and I'll just give a little report on where we are on this work. So the question we're interested in is whether we can build very simple models for this family of materials. This is a model with Dirac cones on both top and bottom surfaces of both layers that interact with manganese 2+ local moments that are don't produce electronic states near the Fermi level, and that the Dirac cones are hybridized with each other. This is very much similar to a model that Anton proposed some time ago for magnetized topological insulators with non-magnetic spacers between the magnetized topological insulator layers. And in addition to these spin splittings that come when magnetism is present, the different Dirac cones are hybridized with each other via parameters, effective parameters that I will discuss. Let me first let me first talk, the question is this model too simple to describe the low energy electronic states? And here's the first sort of test of this model, comparing it with bulk bismuth selenide. And as was mentioned in the last talk, there is the period of bulk bismuth selenide is actually 3 layers thick because of the stacking arrangement. And what this slide shows is that for about a 1 volt energy range around the Fermi level, the electronic states are first of all not very sensitive to the stacking, and that they're pretty well described by a model which includes hybridization of Dirac cones, 2 Dirac cones on the top and bottom of each quintile layer, and hybridization across the band gap between different quintile layers. And so this hybridization across the, I meant to say across the van der Waals gap between the different quintile layers. So the topological, in this simplified language, the topological properties of this material are present because the hybridization between different layers is actually slightly stronger than the hybridization within a layer. So this seems to give a reasonably good fit to the band structure if you just, take these bulk bands and fit them with just 2 parameters, hybridization across a layer and between layers, which this S here is same quintile layer, and D is supposed to stand for different quintile layer. From these bulk bands, you can more or less account for how the thin film splitting of the surface states depends on film thickness, for example. So that's the non-magnetic case, and so the hope is that in this class of materials, for both the non-magnetic states and the magnetic states, you can describe effects like changes associated with, for example, defect densities and things like this in terms of tunable effective parameters. And but this is for this is another example. So this is just the magnetic bismuth manganese, bismuth, selenide, and telluride, MbS, MnBiTe, which if you just add exchange interactions, which spin split the conduction band, basically just spin split the conduction band and the valence band of the non-magnetic material, then the bands will overlap to make a Weyl semimetal. So as is known, when the moments are aligned in these materials, then they become Weyl semimetals. And okay, yeah, maybe I'll show this, see if it works. So this is the ferromagnetic state here, and I'm going to show how these are a 10-layer thick TI thin film in this model, and I'm going to show in this little movie how the bands, the low energy mini bands of the film change when you turn on the exchange coupling to ferromagnetically aligned moments. And so what happens is, the topological insulator surface states disappear, and once the exchange interaction becomes big enough to close the gap, then there's, basically in the mini bands, repeated level crossings, which are crossings of the mini bands of the TI. And of course, as you all know, at those level crossings, the churn numbers of the thin film are changing. So what this is within the model, and it summarizes kinds of properties that that for the ferromagnetic configuration, you get a quantum anomalous Hall effect, and for the antiferromagnetic configuration, for odd numbers of particles, you can also get a quantum anomalous Hall effect, but they're really quite different in character, because in the ferromagnetic case, it's kind of orbitals that are extended across the thin film, basically the finite size version of the Weyl semimetal states. And the churn number just keeps going up and up as the film gets thicker and thicker, whereas for the antiferromagnetic case, everything depends on whether the number of layers is even or odd. And so this antiferromagnetic case is basically the case of a TI with spin split surface states, where let me just say, go to this. So this is a plot with this simple model, and this is an example of the utility of a simple model, if it can be justified, is that maybe you can do more complicated geometries that are difficult to do with DFT, but maybe more so that it's easy to take account of gating and many body effects, and for example, so this is a calculation out to quite thick films. If I look, for example, at the solid blue line, which is a ferromagnetic alignment of moments in MnBiTe, of course, to get to that ferromagnetic alignment, you need to apply a field of about 5 Tesla or so. But you can see the gaps there plotted as positive and negative numbers according to whether the churn number is even or odd. And so this is just, if you follow my cursor, churn number going 1, 2, 3, 4, 5. So churn numbers get bigger, the gaps get smaller, generally speaking, as the films get thicker. And so it seems like this is you know, probably captures much of the physics in many of these systems. I'm not sure if all of the defects can be rolled into these effective parameters. But one thing I wanted to mention, for example, the mystery of the photo emission, we'll hear more about. So this is showing the gap of the antiferromagnetic states. The gap on the surface doesn't matter whether it's even or odd number layers, doesn't really matter whether it's a churn insulator or a normal insulator for an even number of layers. And so, you know, from this model, you can easily conclude that if there are on the surface changes in the sense of magnetization, then there are topological states along those boundaries which are spread out along the surface by about 1/10 of a micron. And I wonder if that can explain the ARPES, the low energy states seen in ARPES. So now let me just end up with two slides that summarize the some of the things we hoped to use these simplified models for. So this is a bunch of different, this is actually a bulk materials, but you can do corresponding things with thin films. These are the orange layers are magnetized topological insulators, and the blue layers are non-magnetized spacer layers, if you like. You know, we hoped that that you could have spacer layers in your system and to reduce the magnetic field that you need to line up the spins and still have Weyl semimetals in bulk, which become churn insulators in thin film form. And you know what this calculation shows is that when you have ferromagnetic alignment, the orbitals spread out, and they sort of sample exchange energies averaged over space. So whenever you put in more magnetic spacer layers, the spin splitting of the states is reduced. Spin splitting at kz equals 0, k perp equals 0, I mean. That has to be big enough to get a Weyl semimetal. And as summarized in this phase diagram, and this is my last slide, you know, the materials we have seem to be just barely Weyl semimetals. And the reason they're just barely Weyl semimetals is because the exchange splitting of the band electrons is competing only with the difference between the intra-layer and interlayer couplings, hybridizations, delta in this figure. And so it's hard to get them further into the topological region. So this phase diagram is trying to use these simple models to look at questions like how can I get better Weyl semimetals, more robust? And the notation here, this notation m equal 1, n equals 0, just means every layer is magnetic. And so this is just manganese bismuth 2 tellurium 4, 1,2,4 compound, which is, as I was saying a moment ago, these red and blue dots. I think the red one is telluride and the blue one is selenide. They're kind of barely Weyl semimetals. And already when you insert just one magnetic spacer, then it becomes not a Weyl semimetal, just an ordinary insulator. So that means in thin film, probably not a Chern insulator. So in tuning parameters, it seems like the best you can do is somehow make the effective hybridization between the layers weaker to move, and that's basically moving in the direction of smaller bulk gaps. So smaller bulk gaps means that when you make it magnetic, you have a chance to get more robust Weyl semimetals. But anyway, that's kind of where we are, and we're listening very carefully to everything people are saying today, seeing if there are some properties of these materials that can be approached with these simple models. So I'm finished.
Thanks, Alan. So I had a question, and then we'll open it up for other questions. So you showed this, I think it was slide 12, where you have the variation gap size as a function of thickness.
Yes.
Right. So am I to understand, so if you have MnBiTe, which is a ferromagnet, that there are special thicknesses where the gap is 0?
Yeah, so this is, in some sense, if you coarse grain things, there's a smooth curve as a function of film thickness, which has, if you can, when the Chern number changes from 0 to 1, then if you imagine in the bulk band structure a cartoon of a finite thickness film as choosing a discrete set of K points. Are you with me? Is that making sense, Rob?
Yeah.
Okay, so then, as you increase the layer number, you're making those K points denser, if you like. And you may happen to get closer or further from the actual K points where the Weyl point occurs. And so that's what this oscillation is.
So it's basically the same as having a Weyl semimetal, and you try to get, right, you get K between the Weyl points where the Chern number is not 0.
Yeah, you want, a film thickness, which is, I think of in my head as a K mesh, where, so this is sort of one of the K points here when the Chern number is 1. One of the K points is between the Weyl points, let's say, right? And so maybe here where the gap is bigger, it's the mesh is such that none of the K points are close to the actual Weyl point. But as you start to pull the second Weyl point, a second K point inside the Weyl point, the Chern number changes from 1 to 2. So just at the Chern numbers where, just at the film thicknesses where the Chern numbers change from one value to another, that's where the gaps are small. So you want to be sort of in between those. So let's say there's a maximum sort of gap at about 4 layers for MnBiTe, where the Chern number is 1, and then there's another maximum around, let's say 10 for Chern number 2, and then you can get smaller gaps for Chern numbers 3 and 4. As you get out here to thicker films, things might depend on details that aren't necessarily describe it precisely correctly, but with the simplified model. But there's a tendency for, certainly for the gaps to get smaller and smaller. You're basically approaching the bulk semi-metal.
Okay. Let's see. We got another question here from Lin. How ferromagnetic, anti-ferromagnetic superstructures like up, down, down, etc.
Yeah, so we can easily look at all of those things. So what we've concentrated on mainly are configurations which we imagine that you can easily generate by simply applying magnetic fields. For example, if you considered a case where you had only magnetic layers, which is the case on the right here, then you have to apply a field of around 5 Tesla to get to ferromagnetic. If, for example, you had this, every 4th layer was not magnetic, then the 3-layer structure would be an antiferromagnet, right? Or it seems like it's actually just barely an antiferromagnet. 5 layers is certainly an antiferromagnet. And then, so the interactions between these layers are strong, but then when you go to the next repeat of this structure, you have this magnetic spacer. So, assume that within each block, you can get beyond a field of about maybe 0.2, 0.3 Tesla within each contiguous magnetic block of layers. You should be able to get control what the majority spin is. Whether you can get things like up, down, down, that might be, I'm not sure how easy that would be to generate experimentally, but it's easy to look at what the electronic structure would be using a simplified model.
Let's see. Is that sufficient, Lin? I'll move on to the next question for Alan. That's okay.
Yes. Thank you.
So, thanks, Lin. So from Nahyun, Joe, for your phase diagram, how can we move one phase to the other? Do you think strain or pressure would work?
How can you move in this phase boundary?
Correct.
Yeah.
Right, Nahyun?
Yes.
Yeah. So, that was the question we wanted to answer. And, I'm looking for good ideas from you. I think some of these, defects in the middle of the layers are an interesting tuning knob that maybe people will perfect over time. But the reason this particular phase diagram is constructed in this way is because imagining, along the vertical axis there is changing the strength of the exchange coupling along this axis between the low energy electrons and the manganese moments. So I assume that you can make that smaller by increasing temperature. Unfortunately for Chern insulators, that doesn't bring you in the right direction. Similarly, I assume that the hybridization between different layers, hybridization across the van der Waals gap, you probably can make that larger by applying pressure. So I've assumed that moves you to the right in this phase diagram. Unfortunately, neither of those two things move you, deeper into the Weyl semimetal phase. So if there's a way, for example, by fooling around with the antimonide content or growth controlling defect concentration, so that for example, it was mentioned, and I was listening carefully earlier this morning, that the coupling between layers gets weaker by putting in antimony defects or thing, if I heard it correctly. So that should move you to the left in this figure and move you deeper into the Weyl semimetal. So it'll be interesting over time to see how many of those, tuning knobs can be perfected. This system, m equal 1, n equal 1 in this notation, every, alternating magnetic and non-magnetic layers. So this is the 147 compound, this phase diagram. And so these dots are supposed to be MnBiTe and MnBs. So in that system, if you could somehow make the effective value of the interlayer coupling smaller, you could make that a Weyl semimetal according to this phase diagram. Yeah.
Okay, we got a couple more questions for you. A couple more questions for you, Alan. Okay, next question's from Pablo Herrero. Alan, do you have some intuition about what would happen for small angle twisting of layers? For example, this may be a way of decreasing hybridization.
Yeah, so that's a good question, Pablo. So we're working that. There is a theory paper on twisting. It should make delta D smaller, and I am indeed, thinking about that that strategy. Trying to look at it carefully within the usual type of Moiré superlattice model that we look at about whether that will actually make things more, move you deeper into the topological regime.
Okay, one more, and then I think we'll take about a 5-minute break for the next talk. So the last question from Kenji Yasuda. I'm confused with the bulk band structure of ferromagnetic MnBiTe. Does the calculation show that it is a Weyl semimetal, not a magnetic TI?
Okay, so I'm not sure what magnetic TI means. You mean by that you mean like the antiferromagnetic configuration? You can use your voice to clarify. Yeah.
In the ferromagnetic state. So my question is, the bulk band gap closes or it's still open?
It closes.
Oh, it closes when it's ferromagnetic.
When it's ferromagnetic, not when it's antiferromagnetic. When it's antiferromagnetic, it turns out that the the exchange interactions with the local moments actually have very little influence on the bulk states. So the antiferromagnetic thin films, for example, are really just TIs with spin split surface states. But with the ferromagnet, if in this simple model, at least, in the ferromagnet, at least in the bulk, the spin splitting of the states at K perp at 2D wave vector equals 0, where the spins are, spin is a good quantum number. The spin splitting is nearly independent of position. So it just takes, if you can see my cursor, these are more or less just conduction band of bismuth telluride spin split. These are the two conduction bands, spin split. These are the two valence bands, spin split. So they cross, and the exchange splitting is enough to make them cross. So it doesn't happen in the antiferromagnet. They're really very, very different.
I see. So the bulk, the spin splitting is large enough to induce the bulk band inversion.
Yeah, so it's very important, actually. The spin splitting is small compared to the typical hybridization, but it only has to be bigger than the difference between the intra-layer and interlayer hybridization. And, I think that is a note of maybe optimism for the tunability of the states, because it actually turns out that the difference in relative terms is, according to our fits at least, relatively small. The interlayer hybridization is has to be bigger than the intralayer to get a topological insulator, and it's bigger by 25% or something. So the exchange splitting doesn't have to be huge to make the ferromagnetic configuration a Weyl semimetal. And a very simple one, as you can see, with only 2 Weyl points.
Nice. Nice. So,
could I ask a quick question, Rob?
Yeah.
So thank you. That was really, really nice. Could I ask you to elaborate on? You made a comment about how the effective model is easier to incorporate many body effects. Could you elaborate a little bit there about what you're thinking or what you're doing?
Yeah.
Open-ended question, not really a question.
I'm just, I've been doing, graphene-like things for longer than I should admit to. If you, for example, in order to make this system, people have done experiments on, for example, 5 or 3, 5, 7 layer thin films, acceptable layer thin films. And you have to apply a magnetic field of about 5 Tesla or so to make the spins line up nearly ferromagnetically. And when you do that, you're really into the regime where you have Landau levels. And I do think the fact that people have seen the quantum Hall effect in these systems is assisted with exchange kind of enhancement of Landau level splitting that we're familiar with from simpler systems that helps gap states become more stable than they would be without the effect of interaction. So that's one of the interaction effects that.
So along those lines, what do you think the prospect is for looking for fractional states in these systems?
I think if you can make large area, reasonably large area systems which have which don't have any, what's the right word, variation in thickness of the film, then I think there's a good chance you could see fractional quantum Hall effect. Now, these materials are, of course, small gap semiconductors. So that means in bulk, they have a lot of very large dielectric constant, a lot of electronic screening. But in the thin film form, it's really the dielectric constants of the surrounding material that's more important. So I think the interaction effects can be reasonably strong in some of these thin films. So yeah. Mm-hmm. That would be a great thing.
So hello, I'm Nahyun. I'm a postdoc with the Professor Adam Kaminsky in Ames Lab. Today I prepare a presentation about ARPES studies on MnBiTe2 tellurium-4 family. As far as I know, this workshop is designed to discuss about these materials and also plan for future researches. Therefore, I prepare a talk in a way not just talking about our recent researches, but more like a review of recent ARPES studies on these materials. In addition, since previous speakers already gave a great introductions on these materials, so I will get to the point right away. So among all the MnBiTe2 tellurium-4 families, I will cover 3 of them today. The first one is the 1,2,4 compound with antiferromagnetic transition below 24 Kelvin. second one is a 147 compound with the antiferromagnetic transition below 13 Kelvin. And the third one is a 1610 compound with antiferromagnetic transition below 11 Kelvin. Okay, then from the ARPES data, what do we expect to see as a signature of axion insulator? When temperature is above the magnetic transition, we expect to see a gapless topological surface state at 001 direction, which is basically a clipping plane. On the other hand, when the temperature is below the magnetic transition, then we hope to see a gap opening in this topological surface state. So let's keep this in mind and let's go to the experimental result right away, with starting from the 1 to 4 compound. So there are at least 8 ARPES papers are out there, though the results are real discrete. So left 4 papers said there's a gap with the gap size of around 200 MeV, which is comparable to the theoretical prediction. On the other hand, the right side, the 4 papers said there's either no gap or if there is, it's very small. So then what's going on? Let's look at the details of each side, starting from the Nature paper on the gap side, because this one has a very detailed analysis. And then I will get to the no gap or small gap papers. So this Nature paper measured ARPES in a synchrotron light source, starting from the 28 electron volt of photon energy at 17 Kelvin, which is below the transition temperature. Here they see the Dirac-like behavior in their plot, and then they claim that there's a small gap feature in between the valence band and then conduction band, though there's some signatures of residual intensity. So in order to understand this a little better, they plotted the EDC curves, which represent the energy distribution curve. So this is basically y-axis are same as the first graph, but the first graph has the intensity with the colors, but the second graph has intensity in the x-axis. So to be more specific, let's say if we want an EDC curve through this line over here, then we expect a huge intensity here and then goes down, and then we expect another intensity comes up as we go through the valence band. And that's what we are seeing on the very right side of this curve. There's a huge intensity here and then goes down and then goes up. And as we're marching through the gamma point, we expect to see the intensity go below the energy for the conduction band and then going up for the valence band. And that's what we are seeing here. So going down and then going up. At the gamma point, what we expect to see if there's no gap is just a single peak of intensity. But on the other hand, what we saw on their gamma point with the red color plot here, they see a dip and 2 intensity peaks around it. So from there, they claim there's a Dirac point gap in this material with the size of 70 MeV. They also measured at 9 electron volts, and they clearly see the bulk conduction band and bulk valence band with the signature of the surface band in between. In order to understand this better, they did a second derivative, and here you can clearly see the bulk conduction band and bulk valence band with the surface band with a gap here. They also measured the 6.3 electron volt, looks very similar, and then this is the EDC curve again. So this is basically same as the second graph, but the x and y axis are flipped. So the x axis is now binding energy, and the y axis is now intensity. Here, this is blue curve is the gamma point EDC curve, and you can clearly see 2 strong intensity peaks from the bulk conduction band and bulk conduction band and bulk valence band. And what's more interesting is there's a dip, and then there's the interesting shoulder comes up in both sides. And they claim this shoulder feature over here is correspond to the surface conduction band and valence band, and the gap size is 77 MeV. So from this data, they estimated the gap size at 0 Kelvin, and they think it's around 200 MeV, which is very similar to theoretical prediction. But what's more interesting is they found that increasing the temperature does not lead to the Dirac point gap closing. What does it mean? They measured at room temperature and they claim that there's still a gap. So to be more clear, there are two more graphs down here. The left side is below the transition temperature and the right side is above the transition temperature. Here, left side, the graph clearly shows two peaks with a dip, and the right side, the graph shows signature of peaks, but it's very hard to say there's a dip, but still they claim that since this curve cannot be fitted with one single Gaussian or Lorentzian curve, so they think that there's two peaks, and because of that, there is a gap in this material. Nevertheless, the intensity of Dirac cones start to grow abruptly when the temperature decreases directly below T0, as you can see in the second figure. But still, there are some signatures even above the transition temperature. So then the question is, why is there a gap above the magnetic transition? And there are many interpretations about this, which I will discuss later. But here in this paper, they suggest maybe there's a spin fluctuations above the transition temperature. After this paper came out, then the high resolution laser ARPES studies has been done, and these 4 papers are about the high resolution laser ARPES data. So in this high resolution ARPES data, they could see clear surface band between the bulk bands. This is above the transition temperature data, and this is below the transition temperature data. So by just looking at raw data, it's hard to say whether there's a gap or not. So they did the second derivative of it, and then they clearly see there's a little bit of a gap above the transition temperature, and there's definitely a gap below the transition temperature. And in addition to that, they also see the band splitting of the bulk bands as it goes through the magnetic transition. This is the enlarged part of the Dirac point, and this is EDC curve where you can see clear two peaks above and below the transition. And some of other high resolution laser ARPES data did the similar analysis, but then they could not see any of the gap forming. So and here, so some of them are showing no gap, and while others show very small gap size of around 10 MeV. Compared to the calculated value of 200 MeV in previous papers, it's actually very small gap. So then the question is, what can give rise to such no gap to diminished gap in this material? The one paper suggests that maybe the surface magnetic structure is different. Of course, when we have an A-type antiferromagnet, we expect a gap, but if it has a different magnetic structure like a G-type antiferromagnet as is shown here, then we do not expect a gap forming. So this can be one scenario. And another paper suggests that the hybridization between mangan magnetic atom and the non-trivial topological state is very weak, since the mangan state forms way below the Fermi energy, which is here at 4 electron volt. So maybe that's the reason, but it's still unclear. Okay, let's move on to 147 compound. Here there are two possible cleaving planes. One is right above septuple layer, and one is right above the quintuple layer. So let's start with the right above the septuple layer. Here it's very similar to 1-4 compound, where it shows a strong Dirac like dispersion. And they measured above and below the transition temperature, and they also did some detailed analysis. And as you can see, there's no gap forming down to 8 Kelvin. On the other hand, when they measured above the quintuple layer, this is a science advanced paper data, they claim there's a huge gap between these two states, and even above the transition temperatures. You can clearly see two peaks here and there. So then again, the question is why there's a huge gap even above the transition temperature. And they also suggest maybe there's a spin fluctuation going on in this figure. Finally, this is 1 let's see 1,610 compound, I'm happy to share our recent result. So in this material, there are three possible terminations. First one is right above the septal layer, which we call TS state. And the second one is right above the one quintuple layer, and we call it as a T1Q state. And then above the two quintuple layer, we call it T2Q state. So we measure the ARPES on all these three terminations, and it shows a clear difference in Fermi surface and also the band structure. And our TFT calculation suggests that all three terminations should have a surface drop point, but unlike the TSV surface TS state where we can clearly see the surface band in between the bulk bands, T1Q and T2Q surface state, this surface state is pushed downward, and also gap size for the TS is 60 MeV, while T1Q and T2Q is 1 MeV. So, which is outside of ARPES resolution. That's why we focused on the TS termination. And then we did the temperature dependence studies on TS termination, which is right above septal layer. And this is above the transition temperature. This is below the transition temperature. And by raw data, it's very hard to say whether there's a gap or not. On the other hand, the TFT calculation clearly shows no gap above the transition temperature and a gap forming as it goes through the magnetic transition. So in our case, we did a little more detailed analysis on our data, and these are the second derivative data. And you can clearly see the gap in below the transition temperature. And as we increase the temperature, it seems like the gap still survive even above the transition temperature, though the size is smaller. And then it finally closed the gap at 150 Kelvin. EDC curve here also shows the such features. If we follow this peak, it goes like this and then going up, and the bottom one goes like this and then going like that. So there's still a gap formed in between two. And 40 Kelvin, even though it's smaller, it's still there. And then 150, it finally closes. So from here, we found the gap size of 30 MeV at 3.8 Kelvin, and it seems like it closes way above the transition temperature. So this is our data. This was our data, and finally, I would like to conclude my talk with the discussion point about materials. So the first point is, even though so we saw all the ARPES data, and then seems like all of them have a chemical potential located not at the gap but at the conduction band. So in the future studies to realize the interesting physical properties, we need to move the chemical potential and locate it at the gap. And one of the way may be antimony doping. So Anand previously asked a question about this, and there's actually a Nature Communication paper about this, and then they claim that they see a band shifting as they move to the antimony side, but at the same time they claim that they do not see a non-trivial topological surface state as they have a heavy antimony side. The second discussion point is, of course, there is some paper that says there's no gap, but if some papers say there's a gap, seems like it persists even above the transition temperature. And what makes that gap survive even above the transition temperature is still debatable. And three possible reasons are listed as below, but this needs to be studied a little more. So with that, I would like to finish my talk, and then thank you for your attention.
Are there any questions for?
Yeah, hi, Nahyun, this is Anand here. So the question I had was that when you make your measurements, how do you know which termination you're looking at, and what is the usual practice in the literature when people are looking at ARPES data from different samples? How do they know the chemical nature of the surface that they're actually probing?
Actually, that's a very good question. So just using ARPES signal, we cannot tell which termination we are looking at. So here we need a TFT calculation, and then by compare with the TFT calculation, we can define this signal is from which termination.
For quick follow-up, Nahyun, the other question I had was that if you, what is the size of a typical ARPES spot in your experiment? And is there any, you know, I could imagine variation between different regions of the sample. So what are the sort of best practices to control that, or how do people know what their sample really looks like over the size of the spot of your sample, of your ARPES beam?
So the ARPES beam size is about tens of micrometer, and again, since we do not have special microscope for some STM at the same time as ARPES, we cannot definitely tell by looking at the sample. But from the signal, we can at least try to isolate each of them. So for the TS termination, it was quite large. So within the large area of the sample, we were able to see only TS termination. On the other hand, when it gets to the T1Q and T2Q, we had a little problem of isolating of them. So when you look at our ARPES paper, then we said that so one of the indication of our band may be from the other termination. But yeah, so that can be a future thing that we need to study or put more efforts on. But right now, just from the ARPES data and not changing too much within certain area range, that's the best thing that we could do, and compare with the TFT calculation.
Thanks very much.
Thank you for your question.
Any further questions for Nahyun? Because I have one, nobody else does. So Nahyun, I know in principle, applying magnetic field and doing ARPES is not good, but considering, say, for 147, you know, a few hundred Gauss, at least the bulk crystals you can fully magnetize. I mean, is it possible to this in, say, like a pulled magnet or something, where you can attempt to sort of remove any surface magnetic disorder? Has that been tried?
So it hasn't been tried because, as you mentioned, magnetic field in the ARPES chamber can deviate the photoelectrons in a way so that the ARPES data can be significantly deviated. But Adam always have an idea that having a single crystal of neodymium iron boron magnet under a very thin one underneath the sample, that way maybe with the domains we can somehow cancel out some stray field and then get not too much disturbing the photoelectrons and get some interesting data out of it. So that can be, we can try that thing. But also one of the advantage of MnBiTe, I think, is also related to a previous Professor Alan McDonald's question, which is about TME effect. So since here it has a TME effect, if we apply electrical field, then we can maybe produce the magnetic field on the system. And that way, maybe we can see some interesting effects of it. But I'm not sure what kind of thing that we will see in this system. But definitely that is a very interesting thing to try, I think. Does that answer your question?
Yeah, thank you.
Okay.
Any further questions for Nahyun? If not, then we can move to the next talk, which is Bing Lee from Iowa State.
Oh, sorry, can I ask one question?
Yeah, go ahead.
Can I ask one question? Oh, so related to the discussion about the gap opening versus gap closing, I'm not sure how much, you know, I want to ask your opinion about how much it depends on the measurement or analysis, or or do you think it depends on the material, but I mean the original crystal, or it depends on the measurement or analysis side?
So
What's your
good
opinion about
point.
it?
Yeah, so good point. So I think all of them can be better. Maybe there's a sample to sample dependence, as Jan told us in the early morning. There's a possibility of many defects in these crystals. But also we realized that this measurement is somewhat very tricky. So this is this is our data on TS termination, and you can see at the comma point at 150 Kelvin there's a gap closing for sure. But then if you move a slightly different angle within like a point 1.2, then you can see start to opening a gap. So it's really the single point instead of the large area. So if you're not doing a very careful studies on this material with the very detailed scan, then it's very hard to, you can't make a mistake very easily. So measurement wise, that's one thing. And then the material wise, that's another thing. Yeah, so there are many, and also the resolution also matters a lot since the gap size is like small. Does this answer your question?
Oh, yeah, thank you.
Okay, thank you.
Why don't we move to talk then? So Bing, are you ready?
Yeah, can you hear me? Oops, it's not the first slide. Okay. Does this work? Can you see my cursor?
Yep.
Yes, you can see the cursor, right? Okay. So, hello everyone. I'll be talking about the inelastic neutron work on this family of compound manganese bismuth 2 fluorine 4, and also the antimony version, and also a bit of 147. So we'll compare things together and gain some knowledge. My name is Bing Li. I'm a PhD student with Rob. So the motivation for the inelastic work on this material is first we can systematically study the strength of magnetic interactions in this system, and we can compare them. And so to understand our inelastic data, we use the Heisenberg model. So here we have introduced this J perpendicular, that's for magnetic interactions in the layer, intralayer. And we also introduced this JC, or J perpendicular, that accounts for the magnetic interactions across the layer or interlayers. And we also have to introduce the single ion anisotropy because we know that the moments are pointing along the C-axis. And there have been discussions about whether the surface magnetism being different than the bulk, as he mentioned. There are arguments about the gap or no gap. So we were wondering if whether there can be any competing interplane interactions which can give rise to a different surface magnetic ground state than the bulk. So that's one of the motivation. Another thing is for our neutron scattering guys. So we were wondering about whether you can have any signature of the coupling between the magnetism of the electronic degree of freedom. What do I mean by that is this material, you have a small Fermi electron gap, electron pocket here. And of course, the manganese hybridizes a little bit with the conducting electrons. So maybe we can see some signatures of such coupling. And we know that in metallic compound, that we have such things called Landau damping, which basically means the magnons are destroyed by creation of electron hole pairs. And this is the signature of the coupling of magnetism to the electronics. So a question we want to answer is can we see any detectable differences in the inelastic neutron spectrum between a topological insulator and a trivial insulator, for example, the antimony version of the 124. And I'll talk about this in the very end of my talk. So we went to the Oak Ridge National Lab to do the inelastic work. And here is a picture of our sample. We have multiple pieces of small single crystals, and they were glued to this aluminum plate. And we designed the holder in such a way that we can measure two scattering planes. And the experiment was done at 1.8 Kelvin. That's the base temperature. So here's the summary of our data. And on the left, what I showed is the scheme of the reciprocal zone reciprocal space, and because in this compound, the 1,2,4 compound, the lattice parameter along C is 10 times larger than AB, so we simplified the notation and projected everything down to in a 2D plane. And along this, so we have 3 high symmetry directions. So the first one is from gamma to M, that's 1, 0, 0 or H direction. In this direction, we can see that you have really sharp dispersions, basically look like the shape of a sawtooth. And another direction is from gamma to K to M to K again, that's the 1, 1, 0 direction. And then in this direction, we have this M shape. And the top of the band is the K point. And here at the saddle point, that's the M point in the reciprocal space. And we also we can measure the dispersion along the L direction. That's basically along L direction. That's the coupling between layers, and we can see really shallow dispersions. And here I'll talk about 3 features. We'll go through them one by one. So the first thing I want to address is we do see a small gap. So by which I mean that you have a gap here, here, and everywhere you can see a gap. And from the gap, we can extract the parameter of a single ion anisotropy, which is about this much. And also the width of the bandwidth along the L direction, that's a small energy scale, tells us basically how large your coupling between the layers are. And even though this number is small, but actually it's kind of a surprise for us because the magnetic ions are basically talking to each other through a van der Waals gap. And because this is a antiferromagnetic coupling between the layers, so we don't think it's a dipolar, even though the energy scale is small. So it must be some other reason why we have such antiferromagnetic coupling. So related to this, we can actually compare the 1,2,4 and the 1,4,7 and learn something about what's going on with this material. So on the top, I showed 1,2,4 again, and at the bottom, it's 1,4,7. And we can see similar things about this family of materials. First of all, the in-plane, the intraplane dispersions are basically the same. So in 1,4,7, you have this sawtooth shape, and it's really sharp at the zone boundary. And along the 1,1,0 direction, again, you have this M shape. But along L direction, you can barely measure anything. This is a very weak. This tells us that the interlayer coupling is much smaller in 1,4,7 than 1,2,4. This is understandable because the ions, magnetic ions, are further away from each other. But what's the surprise is that in this material, you can actually measure a very small spin gap here. So the gap size is way smaller than 1,2,4. Why do I say this is a surprise? Because if you think about the origin of single ion anisotropy, it can be understood by the crystal field splitting by the local ligands. But in the 2 compound 1,2,4 and 1,4,7, the local environments of the manganese ion should be the same. Why would we have different spin gap? That's a question. One of the conjecture here is that maybe the origin of such single ion anisotropy is actually because we have anisotropic exchange interactions. So this is some interesting point to how we should think about this compound. Then coming back to the experimental plot, and the second thing I want to talk about is that you actually have some small effects due to the interlayer coupling, the J perpendiculars. And this gave rise to some change of curvature close to gamma point, which happens here and here. It's not really clear here, but in the next slide. So here I have shown the experimental plot again, and you can see that actually right out of gamma point, you have a change of curvature. And at the bottom, if you extract the centroid of such peak, and you can see that you have a change of curvature right at 1.5 MeV. And also on the left, I've shown the DFT calculation, and the DFT also captured this feature. So what's giving rise to such change of curvature is actually in DFT calculation, as you can see here, you have a lot of small. If you look at the orange points, those are the couplings between layers, and even though they are small, but you have a lot of them, and they can effectively, like collectively, they can give rise to a rather large effective coupling between the layers. That's the green point here, and it's actually an overestimate of the experimental data. So in DFT, actually, you see it more clearly, but in real data, it's not so clear. The point of this is that we don't see any signature of dominating interlayer coupling. So we have a lot of interlayer coupling, and they are all small, but because all of them actually has a contribution to the in-plane dispersion. So this actually creates some complication in our analysis. Okay. So the next thing I want to talk about is this sawtooth shape, which actually happens here at the, you can see it very clear at the zone boundary. It's very sharp. And this actually tells us that we have a long-range interactions in our system. So in the retrospect, this is kind of expected. So because if you think in terms of Fourier components, and if you want to get a triangular wave, you have to have some higher order harmonics. And this actually is exactly why we end up having long-range interactions in the system. So we used the linear spin wave theory to model the system, and you can see that the data and the simulation, this is data and simulation, they agree with each other reasonably good. And I extracted all the parameters here and put them in this table and normalized to J1, which is the leading ferromagnetic interactions in the system. And there are two things worth mentioning here. First, we have a second nearest neighbor J2. That's this one. And it is an anti-ferromagnetic coupling, and this is actually a competing interaction. In fact, if J2 is large enough, you can end up having a different ground state, a different surface state. But 14% of J1 is not large enough yet. So if this is the reason why the surface is having a different magnetic state than bulk, there must be a reason that this has to be larger than what's right now. Another thing is we have J5, which is about 8%. So even though J5 is small, but this is essential. And J5 indeed is a harmonic of J1s. So J5 is along the same direction of J1. And this gave rise to this sawtooth shape in the dispersion. So this made us wonder, what is the macroscopic origin of such long-range interactions? So could it be carrier mediated? So can we understand this system as for example, condo lattices coupled by RKKY interactions? So related to this, I want to show some recent measurement on this 147. So 147, basically, if you think in plane, 147 would be exactly the same as 124. The only difference would be the interlayer coupling. So if you look at the dispersion in plane, you will see that, again, you have the sawtooth shape. So here we did some temperature dependent study. So the temperature is marked here. I'm going to show a this video of how it goes. As we increase temperature, first you can see that the spectral weight collapses, but you still have this reminiscence of this sawtooth shape, and it persists all the way to 100 Kelvin and 200 Kelvin. You still see this feature of the in-plane interactions. So this might be the spin fluctuations that's giving rise to some weird features we saw at high temperature. So on the right actually is a constant energy cut. So if you cut here, you would see a donut shape at close to gamma point, and you can see that as we increase temperature from 2K to all the way to 100K, you still see this feature of the donut. The difference is being that the donuts are now connected. But I think what we could know is that you still have some 2D ferromagnetic correlations within the layer, even at a really high temperature. So for us, the rule of thumb is that if you estimate the top of the band, which is 2.5 or 3 MeV here, and this is equivalent to a temperature of 35 Kelvin or 40 Kelvin. So it's actually quite a surprise. Why would you still have the 2D ferromagnetic correlations at 100 Kelvin, 200 Kelvin? This is actually quite a surprise for us. So the next thing I want to talk about is this anomalous Magnon lifetime in this compound, by which I mean that here, this is the contour plots again, and I did some trick to remove some trivial dependence to enhance this quality of the picture. And you can see that close to the gamma point, if you make a cut along the energy direction, you would get a peak here, and then we use this width, and you can see that the width of the dispersion actually changes as you move along some high symmetry direction. It's really sharp at the bottom, and it becomes broad here, close to the zone boundary. So actually, close to gamma point, the width increase goes like q squared. This is expected, but then it ran into a plateau, so it's a constant near the zone boundary, and we're not sure why this is happening. One of the possible reasons is that there might be some manganese vacancy or some impurities which can give rise to, which can destroy the magnons at a large Q. But another reason which potentially can be more interesting to think about is that maybe the magnons are coupled to the creations of electron hole pairs. And actually there is this old paper thinking about these effects, and they talked about how you can think the manganese-containing system as condo lattices and mediated by RKKY interactions, and you would end up having similar effects. So then our next question is, could you replace? Could you reproduce similar features if you don't have this topological feature, or you don't have the electron pocket? Would you see the same thing in a trivial insulator, for example, in the antimony version of the 124? And we did the experiment, and but this is more complicated than the bismuth version. So the top is again the bismuth, and the bottom is antimony. So here we can see that instead of the old sawtooth-like dispersion we used to have, and there's an extra branch on top of this the lower energy branch. And again, in this direction, the 110 direction, you can also see this signature of the next branch. And along C-axis, first of all, the interlayer coupling is weaker, so the dispersion is barely observable. And you have some signature of another branch on top of this. That's the same thing here. So then our expectation is that this extra branch must be created by this anti-side exchange. You have manganese sitting on top, sitting at antimony sites, and they are coupled antiferromagnetically, and you have a extra sublattice which gave you the next magnon branch. So to extract some information like a magnon lifetime in this compound is next to impossible, but we do see some interesting features which can be important. Okay, so here's the summary of what have been talked about. I showed you about the single anisotropies and the interlayer couplings, and which is a collective effect. And in the 124 and in the antimony 124 and the 147, the gap is practically zero. And it's interesting to ask the question about what's giving rise to the single anisotropy, and whether they have some consequences in the transport measurement. And the most interesting thing for us is, I think, is that you do see the long-range interactions in these materials, and you have to ask the question, why would you have long-range interaction? What's giving rise to such long-range interactions? And it seems like it's robust against the temperature. And then I talked about some weird feature of the magnon lifetime in the 124. And possibly there might be some coupling between the magnetism and the electronic degree of freedom. That's pretty much what I have. Thanks.
Okay, so are any questions? Neutron work. Okay. If there's no questions, then we can move on to the next talk. So this next talk is a brief review of thin films manganese bismuth tellurium system by MnBiTe4 from Argonne.
Are you guys all able to see my slides? Can you see the title slide? I'll just keep it in this. Okay, good. Thank you. Okay, all right. So thanks, Rob. This has been very, very good for me to listen to these talks today. I am probably the only person in this speaker list who's not presenting their own work. So I'll be just reviewing some of the literature on thin film growth of manganese bismuth 2 tellurium and related compounds. And this is motivated, of course, by the idea that if you could imagine making very well-controlled, large area thin films and bilayers and heterostructures with these materials, perhaps you could realize some novel experiments that currently are challenging. Okay, and so we all know the story about these materials, about how the magnetic coupling between the layers dictates what the edge states look like, for example, and a lot of excitement regarding this physics. And a lot of the work, of course, the very nice work that we have seen today has been done either on bulk single crystals or on flakes that have been exfoliated from such materials, from single crystals of these materials. Okay, so and this is something that I just took from a paper in 2019 where they made bulk single crystals of manganese bismuth tellurium, which forms a super lattice with bismuth telluride, as we've discussed already in this meeting. And so you have these septuple layers of manganese bismuth tellurium, and you can interleave them with bismuth telluride layers. And the idea is, in principle, you could do this in some arbitrary sequence. In this particular example, they grew bulk single crystals. And one of the things that I learned about when I was reading these papers is that it's very difficult, in fact, once you go above the M=1, if you will, compound with just manganese bismuth tellurium, septuple layer compound. Once you start interleaving these bismuth telluride layers, it gets harder thermodynamically to stabilize these compounds. And in fact, the window of stability, the growth temperature, I don't have it here, for these crystals was about 600, I think, if I got that right, or 550, something like that. And in that temperature range, to get a single crystal of manganese bismuth tellurium, the window of temperature they have to stabilize was 10 centigrade. Okay, and you can imagine how difficult this is, particularly when you have thermal gradients in your sample, in your growth apparatus, perhaps. And so it is quite challenging actually to get a good, really phase pure single crystal of this material. And so anytime you see experiments being done on these things, perhaps one thing to check always, and I'm sure people are doing that already, is to find out what the actual thing is that they're measuring, because there are other second phases that show up in these materials. So that 10 centigrade window becomes 2 centigrade for M=2, and even narrower for M=3. And I saw some M=3 single crystals, I think, today in this meeting, which is very exciting. But essentially, you are competing from this idealized layered phase. You're competing with the formation of manganese-doped bismuth telluride occlusions. Okay. So you're going to always have some mix of these two in real samples, and you want to minimize that. Okay, so there are not that many examples of thin film growth of this material. I only found actually about 3 papers. There might be more, but I looked for the last week or so, and I couldn't find too many. And this one, the first one that I'm going to talk about, was done at Tsinghua University and at Shukun Shu's extended group. Actually, this is done by Kehei and collaborators. And what they did was they grew just this first paper I'm going to talk about. They grew manganese bismuth tellurium, just the M=1, with no bismuth telluride layers in between. But they did it on silicon 111 and strontium titanate 111 substrates. You have the conditions here. If you're interested, they can get good crystal quality on the surface of their film as it's growing. That's what this diffraction pattern on the left is telling you, is that they have fairly well, if this was amorphous, you just see basically nothing. You see a blur or a ring, and what they're seeing here is these sharp diffraction lines that are telling you that their films are crystalline as they're growing with the proper lattice parameter. So, and indeed, so when they grow these films, it's sort of interesting what they do. Bismuth telluride has been grown by many different groups, and the conditions for growth for that are quite well known and well established. So what they do actually is they grow 1 quintuple layer of bismuth telluride, then they grow, they deposit a little bit of tellurium and manganese on the surface. That's what's shown in this figure A, if you will. So they grow manganese telluride on the surface, and then what happens by some process that I'll show you in a second, this manganese telluride actually buries itself inside the quintuple layer to form one subtuple layer of manganese bismuth tellurium-4. They verify their structure with X-ray. They do TEM, and they claim to find all the things that they're looking for, including manganese at the right places, and manganese has got the right valence, and so on and so forth. So they are able to get the structure that they think they wanted to get. And then they went ahead and did ARPES. As you know, these groups are very well situated to do that. They do their MBE growth, and they have an ARPES system right next to it, attached to it. So they went ahead and looked, and this was done above the magnetic transition temperature. And as we heard earlier, there is some controversy about whether or not there is actually a gap at the surface of these things. They did not see a gap, but they were above the transition temperature, the magnetic transition temperature. So they just see a Dirac cone on the surface, much like they would in bismuth selenide, but it's different. It's not warped like it is in bismuth selenide. This cone feature, if you will, is very much what you expect to see in manganese bismuth tellurium above the transition. They also did magnetization measurements, and here is where things got a little confusing for me. But in essence, they see magnetism, a well-formed hysteresis loop. So this is the A that I'm showing you here, the figure A on the top left. This is for field pointing out of plane, and this is for a 7 subtuple layer sample. They do that, and this is with the extra layer, if you will, that's ferromagnetic overall. And they see a hysteresis loop that they claim is due to this magnetization of that layer. They can track the magnetization versus temperature and establish that indeed there's a Curie, well-established Curie temperature, magnetic ordering temperature. But if you look at what happens when they measure it for the 6-layer sample, which is nominally antiferromagnetic, where you would have expected that they would not see much of a moment, they actually do see a fairly large moment. And this moment is isotropic. And in fact, they see the same sort of behavior, this isotropic magnetization, a background, if you will, in the ferromagnetic samples as well, the 7 subtuple layer samples as well. So, and when they extract their net magnetization, they actually subtract this background, if you will, where they this background doesn't have any remnants, so it almost looks like it might be clusters of manganese forming inside the sample that are not like the other manganese that's there. And it's isotropic in its response to magnetic fields. So there are some issues with what's going on magnetically in these materials, but they do show you all the data, and you can take it or leave it. And they can also use the anomalous Hall effect, as is shown in this middle panel right over here, where they can actually observe the anomalous Hall effect in their sample, and they can gate it with through the STO substrate, okay, the strontium titanate substrate, which is all very nice. So they can show you that their electrons are talking to the magnetization. Turns out this coercivity and that coercivity are not the same for magnetization measurements and anomalous Hall measurements, which is seen on other systems as well. But they show you all their data, say, look, this is what we get. They interpret that in some way, and they say, well, okay, so we've made this material. It looks structurally like what we set out to do. And this was, I thought, a very impressive, in fact, first, if you will, demonstration that they were able to at least grow the right structure and get this magnetic behavior. Okay, so that's okay. So I should just mention that, of course, you expect to see a gap on the surface state with ARPES, but they were above TC, so they didn't see it. Manganese goes inside this tellurium octahedron, if you will, and it forms there's actually a super exchange interaction between the manganese atoms in plane and 90-degree bonds, and so it's ferromagnetic, and that's why the temperature is as low as it is, the TC, I suppose. And then, okay, so that was that. That was basically their first attempt. They did not see any quantum anomalous Hall effect, anything like that. As I showed you, they had also this rather large background moment that they didn't quite explain as to what it was. One thing they did explain is how this manganese burrows in. So when you deposit the manganese tellurium layer on top, apparently it forms this manganese 3+ bismuth 2+ couple of ions. And this is less stable than if the manganese were to just burrow in by one layer and you get manganese 2+ and bismuth 3+. They did DFT calculation. You can see this also just by writing down the electronic configurations, but this is more stable than that, and that's why this forms. And that was sort of nice to know. So if you just had a really high quality bismuth selenide telluride film, and you were to put down just the right amount of manganese and tellurium, then presumably you would get a very good layer of manganese bismuth tellurium on your substrate. Okay, so in fact that is what they did. So in fact what they did was they grew repeatedly this subtotal layer by doing this process of manganese tellurium growth on bismuth telluride, and that's how they got the structure that I was showing you earlier. All right, so then I'll just move on to the next paper that also they came out of the same group. They followed that paper up by showing that you can also just grow this 1-2-4 phase of manganese bismuth tellurium using just co-evaporation. And they identified, so this is not layer by layer growth anymore, you're just evaporating all of the three source materials all at the same time. They used a slight excess of tellurium when they did this. And then what they did was they used their ARPES as a diagnostic tool to understand whether or not they got the right phase. So first, just to show you that, by varying the manganese and bismuth, this paper is not published yet. I just found it on the web. It's accepted. It was, I think, uploaded like a few days ago. So this is quite recent. And so they basically were able to get the right crystalline phase of manganese bismuth tellurium by just co-evaporation. And they have to vary the manganese to bismuth ratio. And so at low doping, they essentially get manganese, doping, manganese doped bismuth telluride. But at high doping, high manganese to bismuth ratio, they begin to get this 1-2-4 phase. You can't really read these numbers here, but what they've done here is that this lower trace is just the manganese bismuth without any manganese, just the bismuth telluride. Then they get the same crystalline phase at low doping of manganese, but when they're up there doping to about 50%, that's when they get this manganese bismuth tellurium phase emerging, their X-ray data. So now using their ARPES, they see a similar behavior. So what they see is that for very low doping of manganese, they observed bands that they associate with manganese doped bismuth telluride. That's these dispersions shown here. These white arrows are pointing to bands that are the manganese doped bismuth telluride bands. Okay, and then around 11%, something happens. Okay, this becomes a blob, and some new stuff begins to emerge. And eventually, at about 50% of manganese to bismuth in their flux, they get bands that look, they identify as manganese bismuth telluride 1-2-4 phase. All right. So this was very telling in the sense that you had a range of compositions where in the middle over here somewhere, where both of these guys are sort of stable and they can coexist. And that is very important to keep in mind when you're thinking about looking at these materials with any kind of probe. Okay. Now, I should say that they were not the first to try this. Going back some years now, this was a group, this is a big collaboration between some Japanese folks and some people in Europe. I think the same group that had that paper in Nature Materials that was shown earlier in ARPES. They grew manganese bismuth selenide actually on bismuth selenide. Did the same thing. They put down bismuth and manganese on bismuth selenide. So they just had a little bit of flux, manganese and bismuth on bismuth selenide. And when they did that, manganese and selenium and bismuth selenide. And when they did that, evaporated those two species on the surface at just the right amount, they were able to get the manganese again to burrow into the bismuth selenide, and they got this one monolayer of this stuff. That's what they claim from the structural measurements. And in ARPES, they see bismuth selenide without the manganese selenide on top. And then when they add the manganese selenide layer, they claim to see a large gap open up at the surface, where the gap is as high as 85 millielectron volts. They They look at this band structure. They calculate the band structure and try to fit to their data. I'm not an expert in doing any of this, so presumably they did it all right, and they get agreement with what they measure. Okay. Now, by tuning the spin orbit coupling, essentially. Now they also measure the magnetic properties of their sample, and they on this particular sample, manganese bismuth selenide. We didn't talk about this material at all today, I think. They do see a magnetic signature from their sample out to high temperatures, but you don't see much hysteresis over here, though the fields are. This is kind of a I don't know how to look at this curve, and I really don't want to criticize the curve. I just want to say that this is there could be some clusters or something like that. I wouldn't be surprised if that's the case, but what they are seeing here is that this magnetism, whatever it's from, is persisting out to high temperatures, and that may be consistent with what they are observing over here. Don't know. Okay. So with that, let me just say that I'm going to wrap up because I just want to. Basically, these are only 3 papers I found online where people have published something about their work with thin films, and so a couple of questions, thoughts that I had while going through this process is, can we improve the temperature of the quantum anomalous Hall effect by trying other things, going to something other than tellurium, for example, selenium. Then one other thing, and a related sort of question, which I didn't ask, I meant to ask Alan earlier, which is that why do we keep using manganese all the time? What are other options? Can we imagine something that would have a larger exchange interaction, or we could maybe dope, have better chemical properties in terms of how it dopes the system, and that might be important. So okay, so chemistry, you could try different chemistries. Okay, if we imagine trying to get a higher temperature for the quantum anomalous Hall effect. Large area of phase pure thin films, like these guys showed from Tsinghua, when they varied their flux for growth. If you can accomplish that and actually show that you can do that for really doing mesoscopics, like the era of gallium arsenide, if you will. But this is very hard to do in systems in complex systems like this. There is no line compound you can play with. It's hard to imagine getting to that level, but I think we should think about ways in which you could improve the phase purity, if you will, and the defect concentration to reduce that or perhaps increase that in your samples to get the desirable conditions. So you could do all kinds of interesting mesoscopic experiments, proximity effects, maybe do optical measurements to look at the quantized magnetoelectric effect, look at Faraday or curve rotation from thin films. But all of this is predicated on having high quality samples. All right. Then, of course, we heard about how important surface magnetization might be and how that could vary from the bulk. And so better understanding of the actual electronic structure of surface states would benefit also from not having too many other phases around, and also having precise control of the termination layer. Okay. So, and then we heard about the superlattices of various kinds using these materials, but that could be used to tune exchange interactions, and also thereby get different novel topological states, perhaps. So all of that could be, maybe we can never go above n equals 2 in any reliable way using bulk synthesis. And so if you really wanted to do it, maybe Pablo and his friends know how to do this with just van der Waals epitaxy. But if you wanted to go and grow this in the lab, perhaps thin film growth with MBE might offer you that opportunity to grow materials that you could not do growing it from bulk. So I would just end there. I had a throwaway slide here. Well, not throwaway. We are pretty close to doing this. Having a vacuum suitcase ready. We've been shut down now for a while. This stuff is sitting out in our lab right now. So hopefully, if everything comes through, perhaps we'll have some samples to send for ARPES and stuff. But most excitingly, if we are able to convince, if we get some resources for doing this telluride-based and selenide-based synthesis in our MBE system, as others are doing as well, there could be new opportunities that would get opened up. So with that, thanks very much for this opportunity to present our literature review, and I'd be happy to take any questions.
Any questions for Anand? I'll throw your way is that there is a recent paper in Nature that I think has similar conclusions to the one you showed here for the selenide, or for the, where you can span basically from the dilute quintuple layer to the septuple layer systems. And they did this for MnBe growth of bismuth, tellurium, and manganese bismuth tellurium, and selenium, and antimony tellurium, I think. And what they find is similar to what happens here, is that for certain growth conditions, you do start to form these spontaneous septuple layers. They're not necessarily always stacked in an ordered fashion, but they do form. And in cases where they form fairly completely, you see the largest gap in the surface state. But I'll send that one along.
Yeah, please do, please do. I somehow missed that. Was this a recent paper in Nature? You said Nature Communications, was it?
It's full on Nature, December 2019. Are the last two authors.
What was the last Europe. Okay, you can send it to me. I'll look at it. I'll look at it. There is definitely.
But yeah, I mean, I think that it sounds similar to what you described anyway. But
yeah. I think it seems to me that there are some very beautiful basic questions that we're trying to answer, and as always, I think it's going to be a little bit of work to get to that point where you can really fully rely on what's coming out of a measurement. My own bias, I guess, would be that if somebody is seeing a gap, that's hard to fool, right? I mean, you can't see a gap, and if it's not there, how would you see it, right? That's one of my questions to the ARPES people. Is there some way to fool yourself about seeing a gap? You could imagine that a state that has a gap intrinsically, there could be some extrinsic things that close it, or maybe the other way around. I don't know. I mean, I don't have a feeling for this. So if I see it and not see it, what should I believe? That was one of my questions that I was kind of trying to struggle with as I was reading the literature on this stuff.
There are two components mentioned, right? One is the intrinsic versus extrinsic gap in the spectrum, and two is detecting gap. So some of the gaps in literature on this material are actually hard gaps. You always have some states in between the two tips of the hands. It seems that the temperature evolution is also very strange, because even in the Nature paper, the original one, this gap close at the end. If you look carefully, there is still a finite change in the weight at the Dirac point as the increased temperature. And we also seen it now in data, and this persists up to 100, 150 Kelvin. No, it's not as clear cut as one would wish. And I think it will require more experimental work and also some theory effort to understand exactly, what is the range of spin fluctuation, how does it affect the gap, and so on. So it's something that needs to be carefully studied.
So since if I might ask a question of this audience, which is, why only manganese, and what other things could we imagine putting into the material that would do something for us differently from what manganese does, perhaps, either chemically or magnetically? I was thinking about europium. Would that be interesting to do or possible to do? I don't know. Has anybody done that in the system? And also, yeah, go ahead.
I was just going to say, I was wondering about the opposite limit of going to a lower spin to remove some of the ambiguity about single ion versus exchange anisotropies, and whether that would lead to more complex frustrated spin structures.
That's a good point.
These materials exist in silica. I mean, people have done DFT calculations, I think on the europium and I think on some of the lighter transition metals, chromium and vanadium. Yan, step in here if or Lin, maybe you guys have seen it as well, but I think there's been some work on those. And of course, these lead variants, which are the non-magnetic septuple layers, which are supposed to be TIs. So somehow if you can use the septuple TIs and introduce magnetism almost like you did with the quintuple ones. I don't know. But, the one thing back to Bing talk is that if you look at 147 or you look at these sort of two-dimensional magnetism, when you get to the 147 where these layers are isolated, there really is no gap. And so what happens is that for a 2D ferromagnet without a gap, you shouldn't have any long-range order. Right? If you do have a strong uniaxial anisotropy, you can stabilize sort of a long-range ferromagnetic layer, like some of these van der Waals 2D magnets. But if there is no gap, then in principle, the system has some, short-range order, which is characterized by some tails, right? And never really get long-range order. I don't know. I mean, that's why some of these neutron scattering experiments are interesting, because you can go from bulk close layers and spread them out, and all of a sudden the gap is gone. So, what's happened? I can imagine that happens on the surface. So there's a lot, and I think, looking at new materials, chromium, vanadium, europium, these are all interesting things to try. Maybe people have attempted to grow them and they haven't succeeded, given how.
Rob, can you remind me, what is this? What is known about the systematics of increasing, the N of the family, and how the gap goes with that? Does the gap systematically get smaller as N increases?
So, from 124 to 147, the gap nearly disappears. This is the spin gap, right? The
Magnon gap, right? So that really does suggest that the anisotropy, magnetic anisotropy, is coming from the, rather weak interlayer interactions, which are weak, but apparently very anisotropic. I don't know if there's any other way to understand that behavior.
Well, tough, because I think if you have, if even the interlayer interaction is 0, if you have a uniaxial anisotropy, you'll still have a spin gap.
Exactly. And the fact that you see it suggests that there isn't any, right?
Right. And so, as Bing was saying in his talk, I don't know how to understand that in terms of sort of the local coordination of the manganese. It would seem that wouldn't be very different. You're just adding extra spacer layers. So why would that be different? So there could be some other reason for it.
What's measured, of course, in the neutron measurement, the gap at k equals 0 is the sum of all magnetic interactions, right? It's not necessarily the single ion, even though it's often interpreted that way.
It's the easiest way to analyze. Yeah, but you're right. I mean, anisotropic exchange, all these things can contribute, and so you need, more than a measurement on a single compound. You need to look at different materials, like, for example, with the additional layers in between, and that can help you to sort of narrow in on what the origin of the gap is, the spin gap. So these things can put on the surface, and I fully believe that, maybe, and if that's true, you just never really have long-range order on the surface. Very good.
So coming back about manganese, so I always have the feeling manganese is special. It's the only 3D transition element that wants to be really wants to be 2+. So it might turn out that manganese is very special as far as doing this trick of finding its way into the middle, for example.
What about europium?
Europium might be similar. might be a little bit similar anyway.
Yeah, I think
So,
there's a PIL paper.
David Boston's on the call. Oh, sorry. Go ahead.
Oh, I just want to say that I think in the original PIL paper, in the supporting information, they do list a bunch of 2+, these kind of cations can go into them, like including europium. So.
I see. Okay. I should look at that. So I had another question for being the earlier talk actually. You mentioned something about Kondo. Is there any evidence for Kondo-like physics in your samples and transport, anything like that, or was that just a sort of conceptual idea that you were using?
Oh, well, I mean, I don't have any transport measurement to support this claim. Well, I think it's not like a wild, it's not too wild idea to picture this manganese containing lattice as Kondo. But of course the temperature scale might be different than other Kondo systems. So I mean, I don't have the data all in all.
Okay.
Yeah.
It's cool. Very nice. Thank you.
Yeah, but I mean, another thing I want to address is you do need to have some coupling between the manganese and the conducting electrons, right? And it depends on how big this coupling, the hybridization of the manganese to the conduction band. So if it's a small, well, you might not see any feature. Right.
Yeah. No, I mean I was just wondering about the covalency of these guys and how much, like when you think about, the usual oxide picture of charge transfer and negative charge transfer and all of that. I just don't know what this looks like here. So I was just curious.
I think the hybridization is not small. It's not an insulator, so it does fit more to that model of having local moments, which do have some sort of insulating, like super exchange coupling through tellurium, but in principle, you have conduction electrons in the tellurium bands, and they may mediate the long-range ones. But I think, as being said, it would be nice to have other corresponding experimental data that would show, for example, that other than transport, where you do see effects of magnetic order and spin flop transitions on conduction.
Yep.
But how to understand all that within a single kind of description, like RKKY or Kondo lattice, I don't know.
You can get long length scales just from the picture that Anand is showing now. If you look at that ARPES spectra, you can see that the bands come close together over a very small part of the Brouin zone. And that, if it just took, that will give long range interactions mediated by the bulk bands.
Yeah.
So for the selenium compound, so in a way, it's not surprising to see that it's still n-doped, right? So in the MnBi growth, is it possible to introduce sulfur to make it like more semiconducting, move the chemical potential?
I actually don't know the answer to that. I don't know, frankly. What ends up happening in these things is the temperature at which you do this is very important. And so you can't arbitrarily put things in because the temperature at which you might be able to incorporate something at a given temperature may be too high or too low for the other guy. So you have to be careful. And I just don't know the answer to your question.
Yeah.
But antimony and bismuth.
Pick up some of these conversations and maybe move to the next talk, and you can continue these sidebar at the end. So thanks a lot, Anand. So the next talk's from Wu. Yeah, I can hear you fine. So he's going to talk about surface magnetism, domain walls, and defects in manganese bismuth 2 tellurium 4. So Weyl, whenever you're ready, go ahead and start.
Okay. Thanks, Rob, for the invitation and also very cool to attend this workshop and I learned a lot. So I'm going to talk about basically scanning probe microscopy, particularly magnetic force microscopy, and scanning tunneling microscopy study of this interesting material, manganese telluride. And so there's a limit of time. I'm trying to talk several things. So let me mention my conclusion here on the first slide. So from the MFM measurement, so what we can infer is that actually the A-type antiferromagnetic order it persists to the surface, as sort of showing in this MFM image. And we see this kind of the termination dependence on up-down antiferromagnetic A-type order, and also across the step edge, across the domain wall. Okay. And another interesting thing we found is that by applying magnetic field, we can actually visualize the domain wall, antiferromagnetic domain wall in this A-type antiferromagnetic order. So this actually we have an interesting impact beyond magnetic field telluride antiferromagnetic domain wall imaging. And finally, SPM, as Yan already showed that we observed the native defects in this field, and also I think there's enough time as we mentioned, we also seem to observe the another native defect which is sitting at the manganese site in the middle layer of this applicable layer. Okay, just briefly mention that we use a both microscopy, it's a homemade system, and also low temperature SPM to study this material, get markers. So first I will present some evidence of this A-type magnetic order, and also the imaging of the antiferromagnetic wall, which due to some possibility contrast magnetism. And for the audience, some of you from UT Austin, so I apologize. This is the same as the seminar talk a few months ago. And also, I will, if there's enough time, I will briefly mention the defect starting using SPM. So, with MFM, we can visualize the formation of this antiferromagnetic domain in this interesting topological antiferromagnetic magnets. And again, the sample from Yan at Oak Ridge, and we have studied three kind of a material from the magnetism telluride and the antimony dope material, and also the magnetism antimony telluride. Antimony telluride. Okay, so all of them below above T-nail, we don't see any domain or domain wall contrast, and below T-nail, we can see there's a domain contrast in magnetism telluride and also magnetic antimony dope telluride. And in addition, there's also actually, if you watch carefully, you can also see that the domain wall has some contrast. And this actually effect is stronger in the antimony end. Okay. And so why we see the domain contrast? Okay, so in fact, in this has been known in the so-called synthetic antiferromagnet material. Then you have a triple lattice of ferromagnet with some non-magnetic spacer between the interlayer coupling, effectively introduce antiferromagnetic interlayer coupling, and there will be when you have this alternating A-type order, up down all the way to the surface, and if that persists to the surface, then there will be a slightly uncompensated net magnetization near the surface, which produces a straight field. Okay, and this straight field with opposite sign when you cross the domain, and therefore you have domain contrast, and very weak domain contrast, much bigger than the ferromagnet, but it's observable in synthetic antiferromagnet. And now what we found is that in this natural antiferromagnet, we indeed can see this domain contrast. Okay. And in addition to see the domain contrast across the domain wall, and we actually also can see this domain, this kind of like basically termination dependent contrast, right? Can also be observed across the step edge. So here is the step edge on S-strong surface. We can see there's a dark, bright, and dark contrast across the step edge, indicating the surface magnetization is one is up, down, up, down, up. Okay, and so here I have a two arrow to the red arrow cut across the step edge, and then the green arrow cut move along the step, right, which you cut across the domain wall. And here, and then from the line profile, you can see. So across the domain wall, you have again this termination dependent contrast, right? And this contrast can be flipped by flipping the two moment by applying a small magnetic field, which is small enough without impact the bulk magnetic property. And therefore, this contrast reverse is really indicating the straight fluid from the sample didn't change. I only switched the two moment. Okay, and also there's a big domain wall contrast, which I will mention on the next few slides. And also, when it cuts through the domains, cuts through the step edge, you see the contrast also reverse when it goes through one setup layer and goes to another setup layer, the contrast reverse. And again, if I switch the tip moment by a small magnetic field, this contrast reverse. So this all indicating what we observe here is the magnetic contrast from this kind of A-type order, which depending on how the A-type order terminates on the surface, either across a domain wall or across a step edge, you have the opposite magnetic contrast. Okay, so of course, MFM is not a true surface sensitive technique, so this cannot this kind of observation cannot really unambiguously say that A-type really terminate to the surface, right? Because you can imagine having a small, a thin non-magnetic layer cover on the surface, which might still let this straight fluid leak out. So to address this issue, we utilize the fact that this material, as Yan already showed, that the surface has some kind of sorry, has a like to have this bismuth telluride impurity phase, which we often dope with manganese. And as we know, this manganese dope bismuth telluride is a very soft magnet in the quartz crystal. So when you have a very thin layer of manganese dope bismuth telluride on the surface, they will behave like a basically essentially like a super ferromagnet, like a very large susceptibility. So that's what we look around in like a relatively larger scan size, and we can see we have this step edge, and then the step edge would like to narrow down on the surface, become like a double step here. Okay, and occasionally you also see this kind of a additional like a hexagon-like shape of decorations. Those are basically the impurity phase magnetic dope bismuth telluride on the surface. And now on the MFM image, you can see when we don't have this kind of when the surface is not covered by this impurity phase, you can see this termination dependence domain contrast across step edge, across domain wall. But whenever this surface is covered by this impurity phase, then all this contrast will be screened. They are complete. They disappear underneath the impurity phase. So they're indicating that whenever you have a surface covered with some relatively soft magnetic layer, even just one or two, actually here is a 3 quintuple layer step height, and that's enough to block the magnetic signal from this antiferromagnet. Okay, so here is a zoom in and also show the line cut profile. You can see basically because manganese bismuth telluride, the 2 quintuple layer height is almost the same as the 3 quintuple layer height. So that maybe that's why they always like to grow a 3 quintuple layer next to this double quintuple layer step edge. Okay, and again, whenever the step was covered by this impurity phase, this kind of magnetic contrast disappeared, indicating the signal is screened by this impurity phase. So therefore, we conclude that although it's not direct evidence, if the surface have some kind of relaxation, like the earlier paper proposed, maybe become disorder or maybe implement A-type or even non-collinear order, then those are usually have a larger susceptibility than the magnetic susceptibility than the A-type order. Then we expect they will suppress this kind of terminator dependent contrast. Okay, so that's the our evidence that this maybe the A-type order persists to the surface, not there's no relaxation. And I don't have time to talk about another evidence. We also observe actually this kind of a surface termination have a so-called surface spin block transmission at the lower field, which by applying field you can see that, but with time limitation, I will skip that. Okay. But that also indicated this A-type order does persist to the surface, which suggests there might be no relaxation suggested by other papers. Okay, and also as we also observed in this material is that the domain size are typically large. Okay, usually it's many micron, or sometimes even tens of micron. So the domain wall will be the density of the domain wall will be relatively small, so that they won't be able to explain why there's observation of a gapless surface state in ARPES. Okay. Now, another interesting byproduct why we are turn on magnetic field is that we observe that the domain wall contrast actually getting stronger and stronger, especially able to higher and higher magnetic field. So in this particular case, I'm showing antimony dome sample, which shows a much better contrast of the domain wall. Okay, and as you can see, this domain wall contrast increase almost linearly with the applied magnetic field. So, and also as we're approaching the spin block transition, which is about 3 Tesla, the domain wall getting soft and be even manipulated by MFM tip. So we have to pull the tip away in order to stabilize the image. So why we can see the domain wall contrast in the finite magnetic field? As we know, when we have an up-down domain, and then down domain, this is the anti-phase domain. When you go from one domain to another domain, right, the domain wall, the spin inside the domain have to turn around, right? Either in a nail type like we show here, or it can be a so-called block type where the rotation plane is perpendicular to the is parallel to the domain wall, right? Plane. But nevertheless, in the middle of the domain wall, the spin will be forced into a block state. In other words, the spin will be parallel to the AD plane. Okay, and as we know, if the spin was forced to lie down in the plane, then we have in the spin block state, you have a higher susceptibility. Okay, and higher than the unblock state, the A-type order. So therefore, when you apply increasing magnetic field, that this kind of a domain wall will have a high susceptibility. Therefore, then you have a larger magnetic signal. You see here. So this kind of spin structure actually usually difficult to visualize, but in some rare case, like spin STM, is a seminal work by Matthias Boden, and also showing that this kind of spin in the antiphase order, the spin rotate, right? And then in the middle of the domain wall, the spin is perpendicular to the spin outside the domain wall. Okay, so so in terms of magnetism, and we expect this is a very general idea. Okay, by the way, we also see the same behavior in this domain wall content in all the compounds from manganese therride, antimony dope compound, and also pure antimony compound. You will see this kind of effect when you finally fill the domain wall content increase. So therefore, this can go beyond this MnBiTe class of material, that if the material have a uniaxial anisotropy antiferromagnet, then we can use the same idea to observe the domain more. I think this is something interesting and go beyond this class of material. Of course, if we can see the domain more, right, with this MFM, especially ferromagnetic field, then as you know, in theory, there's also edge state propagating around this domain more, or the step edge, as previous speaker talked about. Right? So this will be an interesting way to find the domain wall and the step, and then to try to visualize the chiral edge state at the domain. Okay, so I think I'm running out of time, so I just briefly mentioned that with STM we can see this native defect in this material. One problem in this material, as again and others already mentioned, that there's a lot of defect in this material, probably related to very narrow growth windows. And for example, here the dominant defect we observe on this magnetic telluride is this manganese and the bismuth anti-side. And also this some bismuth goes to the beryllium side as on here. And also one important impact by the defects that although there's no clustering of this anti-side, but due to fluctuation by random doping, there will be some region this manganese get closer to each other, and when they get closer to each other, they actually suppress the conduction band spectral weight, as shown here. So, in fact, this kind of anti-side local density does correlate with this kind of reduced spectral weight local density at the Fermi level. It is at the bottom of the conduction band. So there's also influence of basically the density electronic fluctuation in nanometer scale by this random doping of the manganese anti-side. So that could also impact the observation of ARPES and other transport. Okay. And finally, I don't know the time, just briefly mentions because of the defect density is relatively high, difficult to look for different defects like the defect in the manganese layer. And using spectroscopy mapping, we do see indication of a defect state, which is formed in a triangular shape. And in this kind of a triangular shape, having this kind of a peak at about 18 millieV below the Fermi level, it seems to have about 1 nanometer size or 1.3 nanometer size defect in the topography. Okay, so they're indicating this kind of spectral wave peak is coming from a defect in the quartz layer, in the manganese layer. So compare this with the DFT calculation by Mahua and Oak Ridge, right? So we suspect it's likely bismuth replacing the manganese defect from anti-pack defect. Okay, so I think I didn't talk too much, so let me just maybe skip. I mean, there's some other STM work in the literature, but more or less seeing similar results as this observed. So let me just come to my conclusion of the outline. Okay, so using magnetic imaging, we see the A-type order actually seems to persist the surface to the MnBiTe, and so those kind of seem to exclude those speculation or surface relaxations of the magnetic order. And also, using polymagnetic field, we can see a propensity contrast between the domain and the domain wall. This can be an interesting mechanism to visualize the domain wall in other uniaxial antiferromagnets. And also, the defect that certainly is an important issue in this MnBiTe family, and I think STM is one of the useful calculation tools to correlate with the growth and other techniques and to optimize the quality of this MnBiTe system. Okay, I guess that's the end of my talk. I'm welcome your question.
Okay, thank you. Questions for Weyl?
I have a question. With that, did you measure 147 to see whether the anisotropy is still there?
What is still there?
Anisotropy, single ion anisotropy. According to Bingley's spin wave, it seems the anisotropy is gone. The gap is gone.
Oh, we does have some preliminary result on the 147. Apparently, as some of you might know, scanning probe is very slow. So we have done some measurement on MnBiTe124, but 147 we did some measurement, but not very conclusive. But I would say the anisotropy is still there, and I mean we can still see this kind of combination dependent contrast. But there's a little more complication because there's an additional telluride layer, right, which also has some manganese anti-side in there. Actually, they could also become magnetic, and so is at this moment, because we don't have enough study to say for sure, but judging from the zero field or low field data, they still have this kind of combination dependent contrast. So I would say that anisotropy is still really strong. And related to that, why neutron seems to see this collapse of the spin-wave gap, I was wondering, I mean, maybe Dean can explain, maybe think about whether it's, or Ralph can think about whether it's reasonable or not, is that, as we know, when you're including another layer of a bismuth telluride, right, the interlayer coupling becomes weaker, and sometimes it might be even become more ferromagnetic-like coupling between the physical layer or MnBiTe. So I wonder, when you have this competition, right, as you also mentioned, in plane, there could be an anti-ferromagnetic exchange competitions. I wonder whether that for the outer plane, the interplane coupling, when you make the layer further away from each other with this telluride, the spacer layer, you might maybe have some competition between this original anti-ferromagnetic interaction and some ferromagnetic interaction. And that competition, whether that will sort of give you the kind of a softening of the spin-wave gap. So in that sense, it's not intrinsically the anisotropy reduced, but maybe because of magnetic exchange competition along the C level.
Hey, Weyl.
Yes.
What do you know? Can you estimate the density of anti-side defects, per layer per area, and does it correlate with the position of the Fermi level? Could they be the main dopants?
Good question. So, so yes, I mean, the simple answer is that what we observe is on the surface. Actually, this anti-side is on the second layer, and so we cannot really see the directly the deeper layer. That actually the sixth layer it should be the same, right? But the defect would be much bigger to see. But just based on if it's due to the random cleaving, right? This is low rate of similar density, so I would expect this anti-side is uniform, homogeneous, randomly doped into the sample. It does no strong clustering tendency as far as we can tell. Now, whether there's some Fermi level fluctuations. So the strong effect what we see here is that, especially for this manganese anti-side, is that it suppresses the density state of the induction band bottom. So that may be because of there's a lack of a p orbital in the manganese. And also, you can also see that the whole spectrum seems to slightly, I mean, it's hard to tell for sure, that shifts slightly toward the high energy. So meaning the manganese andesite also have a little bit of a like a whole doping tendency. It's also consistent with the DFT calculation, right? So there will be some also blocking order for maybe it's hard to say because it's hard to tell exactly where is the band edge from the spectroscopy. So if you may have like several tens of milli fluctuating possible, but we cannot say for sure.
Okay.
Okay, further questions, we'll move on to the last talk. This is from Ken O'Neill from Los Alamos about optical and high-field response of manganese bismuth tellurium compounds. So Ken, whenever you're ready.
Yes, can you hear me and see my slides? Okay, so I'm Ken O'Neill. As Ross said, I work with Dmitry Yarotsky at Los Alamos. We've kind of teamed up with Ross McDonald from the Magnet Lab to give a summary of what is and is not done for the optical and magnetic properties of these materials. So starting with the optical properties, pretty as far as I can tell, besides all the ARPES that Nahyun beautifully summarized earlier, there hasn't really been much done in terms of optics or ultrafast or even general spectroscopy on these kind of materials yet. So I want to start by just giving a couple examples of how optics can be used to study these kind of topological materials. So first is an example looking at the quantized Faraday and Kerr rotation. So this was a work done in Science a few years ago on bismuth selenide. So what they do is they send a polarized beam of light through a material and check the rotation through how the rotation of that polarization changes through transmission or reflection off the surface. And what we see on the right is they measure different quintuple layers, so different thicknesses of these samples, and they apply magnetic field. And you can see these nice flat areas at the low frequency in the terahertz region where you get this quantized effect. So it's all one value. As you get to the higher, the thicker layer numbers, this region where that occurs becomes more narrow and requires slightly higher fields. And they see this in both the Faraday rotation on the top and the Kerr rotation on the bottom. And this happens at fields that's lower than the quantized resistance response shown in this top right inset. So this is one way that we could probably use optics in this material to look for these quantized effects to show that it's topological. Another possible way to do this is with high harmonic generation. So if you illuminate the material with a bright, say, middle infrared pulse or beam, you can look for different harmonics and see kind of the pattern that comes out. And what this group theorized is that you can see a difference between a trivial state and a topological state, whether you use a linear polarized light or a circular driver. The circular polarization light has a much more different response. So you can see the topological on the bottom here, the red curve, or red dashed line is much higher than the blue one, where the cutoff is for the trivial case. And moreover, if you look at the circular dichroism, so sending left circularly polarized light versus right circularly polarized light into the material, in the trivial phase, you get a slight difference you see some dichroism, but that is a much larger effect in the topological case. And on this bottom plot, this C is the Chern number. So in the middle, we have kind of a topological phase, and on the right is on the ends where the Chern number 0 is a trivial phase. So you get this nice kind of even value in the topological phase, looking at all these different orders of harmonics. And as you go into a trivial phase, this dichroism can either vanish and go towards 0 or even switch signs. So we could think about ways to use this to kind of look for these trivial topological phase transitions. So there's two options so far that have been kind of not proven, but put forward as ways to look at these topological materials. So we kind of made a list of things that we could think about doing for this manganese bismuth tellurium, and kind of a list of what we are capable of doing and what might be interesting. But I mean, there's obviously room for discussion on these. So we could look at this look for this quantized Faraday or Kerr rotation. We could apply magnetic field to do this. We could also look at different layer thicknesses. As many people have shown before, the even number of layers show a different effect than the odd number of layers. So that could be interesting to look at. We could do this high harmonic generation in an applied field to kind of drive from a topological to a trivial phase and look for this phase transition. We could also use like an intense terahertz pulse and the magnetic field component of that to drive changes to the spin texture and see how that changes the transport properties and see how that affects the topology. We could also imagine pumping a coherent phonon with light to kind of look at to play around with the exchange interactions within the plane or between planes, depending on which phonon we choose and what's available in the material. And we could also look at kind of more broadband optical properties, and again, applying magnetic field. In this case, we would want something low energy to get near the Fermi level, because that's where most of the physics is at. So if the samples are large enough, like if we could make a nice big thin film, we could do terahertz in magnetic field. Or if not, if the samples are still kind of small, we could do maybe transmission or reflectance, just kind of FTIR, Fourier transform, infrared spectroscopy, and a magnetic field at the Magnet Lab in Tallahassee. So there's a lot of open area for these optical properties still. So there's a lot we can do and a lot we probably should do. In terms of high field work, there's some really great work on the quantum anomalous Hall effect. And I believe Rob even showed this figure in his introduction. So here they're looking at devices on exfoliated samples. There's 3, 4, and 5 different subtuple layered devices. And depending on whether it's an odd or an even numbered device, you get a different response as shown on the right here. In the odd number cases, you get these kind of plateaus where you get these magnetization kind of plateaus as one layer is kind of flipping its spin and locking in for a short field range. What's important to note here is that they're reaching kind of this quantized resistivity or quantum of resistivity at relatively low field. So this happens by, say, 5 Tesla. And here it's even happening without gating the material or the device. And these odd layer devices show these hystereses around 0 field. So where they've kind of stabilized a quantum anomalous Hall effect at 0 field. If you take, this is more data on the 5 subtuple layer sample. So now they're applying a bias, and that changes the quantum anomalous Hall effect. You get kind of an almost linear response in this red line if you apply 100 volts. As you apply slightly more than that, you get these weird intermediate regions. And then when you apply a negative 200 voltage gate in this device, you reach this quantized limit. And then even as they remove the bias, it stays, because the hysteresis is large, you retain almost a quantum of resistance even at 0 field. So one question we had thought of is, can we chemically tune the material to induce this even at 0 field? So we had been, some people had mentioned there's different ways to play with the chemical or the elements that are in here with antimony or selenium or whatever, what have you. So that's something we can think about. Oh, what would be the best way to maybe do that? Another study, this one with nanoletters this year, combined a top and a bottom gate simultaneously. So for example, on this left panel, they're leaving the back gate at a set value and changing the top gate voltage. And what you see is that this hysteresis in the middle flips sign. So at 0 voltage, say, if you come from 0 Tesla and apply field, you get a decrease. Whereas at this top curve, if you do the same thing, you then have an increase. So you have a reversal of this hysteresis loop. So you can control the sign of your 0 field quantum anomalous Hall effect based on your kind of voltage history. And they can do the same by holding the top gate voltage constant and changing the back gate. So there's different, they have different values depending on which you play with, but the effect is just about the same. And this may be related to being above or below the Weyl point. So some possible experiments we thought up or things to think about going forward is 10 Tesla is more than enough for most of these measurements, especially if you're doing, like they showed, the 5 subtuple layer sample. If we start getting to thicker samples, like a thin film that may be thicker than that, it may require higher fields, but still probably not too high. But one thing that might be interesting to do is to drive to higher fields still, like at the Pulse Magnet Lab, up to 60, 65 Tesla, to look for things, for effects that come from things beyond just the simple spin rearrangements. If there's some underlying physics that is not being studied yet, we could maybe see that. And also we could do some high field transport to directly correlate with any optical measurements we do in field. So I think with that, I will end and kind of open up for discussion.
Okay, let's see. So, I mean, I just have an obvious question. Why is nobody doing optical characterization on these materials, and why aren't we coordinating an effort sort of right away? I mean, Yan, have you been working with any group on the sort of on the optics stuff? Because I think with Ken and Dimitri and these guys can jump right in on that. I think if they had samples. I don't know if Yan's still on.
Yeah, I'm still here. No, I think the only one is the guy from being arrow want to measure the optical conductivity, but not really other things.
How large an area can we have a sample where we have a known thickness, i.e. an odd versus even number of layers? Because that may limit the ability to do the optics if it's looking for things like quantized Faraday or Kerr effects.
Because you transmission, you're saying. I mean,
not necessarily that you need transmission. So Faraday or Kerr is just transmission or reflection of manifesting the same thing, but you would need the spot size for the optics to be big or to be smaller than any step height. So if we were looking at the difference in potential quantization between 5 or 6 layers, as you would need the spot to be just looking at an area that was that size. And I think that's in immediate competition with wanting to move to longer wavelengths to be able to look for these quantized states. So I think that's probably part of the challenge why people haven't jumped on this as much as some of the other measurements. I don't know, Dimitri or Ken should probably comment there as well.
Yeah, I think you're right, because again, a lot of the interesting physics is going to happen at low temperatures or low energy. So we need bigger samples to use kind of those wavelengths. I don't know if Dimitri has
So
more to add.
what size are you talking about? You say you need sort of it to be no terraces over some fairly large spatial scale?
Yeah, so for terahertz with measurements, we would need probably 3 millimeters by 3 millimeters.
Number of layers.
Yeah, again,
yeah.
Rob, I think that's, if you're serious about going after the, looking at the quantization of those effects as a function of layer thickness, then that would become important. There's probably still room for just looking at bulk optics, I think, but again, I don't know exactly. Yeah, there's various levels of hanging fruit, but the exciting ones put pretty strict demands on sample and area and optics, I think.
MBE space, maybe.
Right.
I think I know.
Yeah.
This had to go, but because I guess the exfoliated ones, Kenji said 50 microns is about, as big as the getting now. So you need 100 times bigger than that on the edge.
For low energy measurements, yeah. So for a 50 micron sample, we could probably do some optics, like some ultra fast optical probe, optical pump type work. But to get to the really exciting low energy physics, we need bigger samples, yeah.
I think Anand, he put together this review, obviously not because he's working on it, but he's interested in working on trying to grow these films. And so, within CATS, whether there's there to, as we've done in the past, try to coordinate this thin film growth with the optical and terahertz. So,
yeah. Hi, Rob. I'm still here. So I'm about to head out. Yeah. So yes, indeed, it would be very nice. I think there are opportunities here for sure, and it's indeed in this area where you want to have large area thin films. There's an advantage to doing that, and also to control terminations, and hopefully also to sort of be able to play with things like defects in some rational way. Those would all be very good to do. I'm not, yeah. So that's just the sort of broad statement, I guess. Not very useful, perhaps, but yeah.
There's another question posted here. Oh, I guess it's been answered in the comments, but Peter was asking about second harmonic generation studies and what are the sample requirements there. And Dimitri answered that hasn't, but you need sort of 100 micron samples, so it's a bit maybe more achievable. Anyway, I think there's in the room, maybe some of them have left the room, but were in the room before, where you folks down there at Lannel and Oak Ridge and Argonne should probably be talking about maybe coordinating some optics experiments, and maybe even Kenji and the MIT folks. Everyone's got their way of preparing these samples for different kinds of measurements, and I think the discussion there should continue. With the high field as well. Now, I thought there was some high field stuff. Alan had mentioned this, and he's had to go too because we ran a little over, but that there was some higher stuff where they started to see effects that sort of went beyond this churn insulator picture, right? They started to see Landau levels. And I thought it was above 20 Tesla. There's some recent work done in the high field stuff. And they had a phase diagram where they had these different churn phases. You guys know about that, or have you? See if I can find.
I don't know exactly what you're referring to, Rob, but I think for the thin films, once they're in that sort of quantized plateau, when field has driven it there to a quantum of Hall conductance, that's effectively in that limit. No.
The Zeeman energy scale was coming in, and there were additional phases at high field. I'm trying to see if I can find that.
As you then close the gap closing argument about the transition to a Weyl semimetal. Is that what you mean?
You know, I'm not going to say because I don't exactly remember what's in the paper, but it's on the archive.
Okay, maybe that's a good one to share for us to follow up with.
Typical church later phase with broken time reversal symmetry. And let me see how high of a field. They went up to 60 Tesla. They have maps of this sort of Landau level maps, I guess.
Okay.
And some
yeah,
theory
please share that.
Have,
I'd be very interested to see it. I've missed that one somehow.
But you're right. I think that at some point the fields are large enough that they close the bulk gap, and so then they can get additional phases. Yeah, I'll forward it along.
Yeah, because that then ties into some of the things we were thinking about with, for the TI state, a relatively small field, the superconducting magnet fields below 10 Tesla, seems to be enough for all the gating ranges to induce, this Hall effect, and polarize the bulk spins. But whether or not there was then the possibility of any fractional type physics before you just close the bulk gap, that wasn't clear or obvious to us. But if someone's done some measurements in that field range, that'd be a good place to start looking.
Yeah, send this along to you guys, and you can have a look and tell me what you think about it. This was, yeah, it was recently. I don't know if it's been published yet, but. Oh, let's see. Well, we've run way over here, and I think, for those diehards, the room's available here. This chat room, this conference room is available till 3:30. I think, part of what I wanted to do was really to, as we just did here with the optical stuff and maybe some of the high field stuff, is discuss, where we think there are some well-defined questions that we might be able to go after collectively as an EFRC or in collaboration with, some people outside the EFRC, many are participating in this workshop. And, what I really wanted to do was kind of open the floor and try to get some feedback from people about, the kind of work they want to do and maybe the people they want to try to connect up with. So does anybody have anything they want to discuss? Any ideas about what to do next? If everybody's burnt out, we can say, take some time to think about it. I'm going to certainly all this has been recorded, so we can put the the work up on the web when the video is decoded, and you can go back and kind of look at it and listen to a lot of the discussions we had during the workshop. But I'd really like, to figure out a way for people to come together afterwards, either one-on-one or in small groups, and try to, work out some good ideas or experimental or theoretical work on these things. And so anybody want to offer to, chat with some people after the workshop, or I'll try to write up a summary and maybe that will start some discussions, but just call it good.
I have a question to the theorist, maybe Anton or Peter, regarding the TME effect. So basically, what kind of signature do we expect from either transport or even ARPES? So if we apply electric flow, then what kind of electronic structure changes do we expect from there through the TME effect? because I think a TME effect is quite important thing in these materials. So want to proceed in that way, but kind of hard to predict what do we expect to see or how to proceed further in experiments.
So ARPES experiments, I mean, are you trying to think about whether you could see a signature in ARPES?
Yeah, so like if we apply electric field, then there's some kind of a response in the magnetization. And so maybe do we expect some changes in electronic structure as well? Or if so, then what kind of thing that we can expect to see, something like that? And also, is there a way that we can detect that kind of effect more clearly in the transport measurements?
Yeah, I don't know if you can see this in ARPES. I mean, well, I guess TME means that you will get orbital magnetization in response to electric field. But I don't think one can. Well, I don't know. I need to think about that. But off the top of my head, I don't think one can see that in ARPES.
Then the transport can see.
Well, I mean, no, you can see. I guess the effect is that you're going to see magnetization in response to electric field.
Right.
So.
So you would pick this up with a squid or something like this, with like a local device? Or?
Yeah, for example.
I also don't really have a good answer out of the top of my head to this question.
Yeah.
And still on? I guess, one question that I have is, what is the status of these magnetic, using magnetic ions other than manganese in this structure class? I talked with David Johnston, and I don't know if he's on. He was on earlier, but he's been doing a lot of lately growing different europium triangular lattice intermetallic compounds. And sort of, even though he's not in CATS, a lot of what he was interested in was kind of converging on the same materials. And we talk a lot about manganese, bismuth, tellurium in group meetings and things. And so he's been encouraged by that. And I think he's going to try to grow some of the europium crystals, europium, bismuth 2, tellurium 4. But, where do you think some of the other ones stand? I mean, we talked a little bit, I guess people mentioned some of the lighter transition metals. Is there any real effort to try to grow variants of this structure, magnetic variants?
Yeah, I tried. Can you hear me?
Yeah.
Yeah. Okay. I tried actually on the 3D roll. I tried most of them, but it's pretty interesting once you change manganese to something else, whatever. Cobalt 2 plus, you expect that might be 2 plus, iron 2 plus, whatever. The phase is not right anymore. There's something else will come out. So the structural stability might be something that's preventing the formation of other phases or other magnetic ions. For europium one, I tried, but not really hard on that. I think the same kind of problem. The phase is not really always. It might take quite some effort to really get the right phase.
Maybe if you're doing other things, maybe you can talk with David Johnston, and there could be some information swap there. Maybe he can try to focus on that if you're not doing it.
I'm not.
And you can kind of.
Yeah, that's not my focus at this time. I got quite something else to play with. But I can email to David, so I can explain to him what I did on the European one, why I failed, and my understanding why I failed, something like that.
I think he's willing to try it. I know that he also grew this europium magnesium 2 bismuth 2. I can't remember which one it was, but it was similar to this europium indium 2 arsenic 2 and europium cadmium arsenic 2 triangular europium intermetallics, and that one's also supposed to be topological material. He made some of those, and he has some stuff out on that. Anyway, so that's another possible direction there.
Yeah.
Different substitutions as well on the manganese 2 tellurium 4. Obviously, antimony is interesting, but did you try some other ones?
Bismuth by antimony, tellurium by selenium. Tellurium by selenium definitely not working well. There are some, well, what we can put in at this time is, for example, tin or lead to the manganese side. But that will dilute the magnetic, disturb the magnetic interaction. TC will be lowered. And one good thing is the critical fields required to flop the spins is reduced also. What other successful doping or substitution? No, that's all. Yeah.
All right. Any other questions or discussion points? Check out. People are free to stay as long as they want if they want to have some other discussions. But I encourage people to walk away from this meeting and reach out to some other people in CATS or elsewhere and try to come up with some experimental new ideas. Other than that, I want to thank all the speakers for presenting their work and doing a review. And I'll talk to y'all soon. Bye.